Good morning. Good morning, everybody. Welcome to the second day of the summer school. I'm afraid the weather is insisting, but I've got some inside information that later on today is going to change. So perhaps tomorrow is going to be better. Today's session is requirements for optical interconnects, the industrial perspective. We're going to have a lot of industrial talks in this session today until the end. First, I would like to call Richard Pitwon from Seagate to talk to us about optical interconnects in data storage systems.
So, good morning, everyone. Just a quick note. Seagate, until very recently, we worked for a company called Xyratex, which is a reasonably large company. It was the largest data storage systems provider in the world of OEM systems. We were acquired about 2 months ago by Seagate, so we joined Seagate, which means that as part of Seagate, we have the disk drive fabrication and then the disk drive deployment and the disk drive test. So it's the whole life cycle. So it's fortunate for me because it means I can use a new template on the previous presentation. So I'm enjoying it, and it's a better template as well. So what I'm going to do is I'll give you a review of the photonics research activities that we've been carrying out within Seagate CSS, that's Cloud Storage Solutions. And that is basically the division that Xyratex became. And that's the division that deals with all sorts of with data storage systems. I will give you an insider's view from a designer perspective of what the fundamental limits are we see for high-speed electronic signal conveyance within a system, and how we see embedded optics in the system addressing these difficulties. And then I'll be talking about the trends that we're seeing now of how optical interconnect is migrating from outside the box and starting to penetrate into the box, which is important because that opens up a whole new ecosystem of technologies, including optical circuit boards. I will talk about some our recent research, predominantly a demonstration of a fully optically enabled data storage system platform and the whole ecosystem of components that made that possible. And finally, a very brief word about our collaborative research and development. So our photonics research and development activities have been ongoing for about 11 years. And there are 4 pillars to this activity. So I've got a pointer here. Oh, I'm sorry. Where's the doing a lot of pointing, so I thought I'd better let's get that. So we have 4 pillars. We have future data storage technologies, and that is looking at our data storage systems and working on how we can optically enable them, how we can work to make them suitable for the next generation of bandwidth density. We have advanced research and innovation, and this is looking at all sorts of things from transceiver design to advanced connector design, to optical waveguide design and characterization. We have network ecosystem and standards, and for this we're engaging with international standards bodies on things like optical circuit boards and connectors, and we are maintaining a strategic presence in the emerging system technologies market for optical interconnect, so transceivers and connectors. And finally, collaborative research development activities. We're very active in the EU, as many of you know. In fact, the summer school itself is organized by, as part of an EU project called Foxtrot, and that we're, of course, members of that. I'll give you a brief description of some of the projects we've been associated with. First of all, the term system embedded optical interconnect, which I'll be using a lot in this presentation, basically means all the technologies required to enable optical interconnect within the enclosure. So I mean things like optical circuit boards with embedded optical waveguides. I need optical transceivers, which are embedded in the system, so mid-board transceivers, and optical connectors. Modern data centers. So, excuse the simplification compared to Professor Varivagios' talk yesterday, but when we think of data centers, basically what we're thinking of is a collection of three fundamental components, and that's compute, memory for the compute, and storage. And these components exist in different ratios. And the building blocks of the data center could be things like simple data storage arrays. You need a lot of storage, of course. Integrated application platforms where you have a lot of the compute. So this would have a server and this would have storage. You would have storage servers, which are higher-end servers dealing with a lot of storage, different tiers of storage, hot, cold, and lukewarm, and high-performance computing and high-performance storage. These are basically the building blocks of your modern data centers. A trend we're seeing increasingly now is, in the past, data center operators had a rack and a certain combination of equipment, and that was what they were stuck with. And it usually resulted in what was called over-provisioning, which meant that if the user had too much of one thing and he wasn't using it, that's just tough. It was wasted. Now we're seeing greater flexibility being introduced into the data center, where users have the choice to use only exactly the parts that they need and not over-provision at all. And one of the ways of achieving this is called disaggregation. And this is where you can take the blocks and you can geographically disperse them. So the blocks allocated to a given user can be geographically dispersed, but this means that you need very high bandwidth density connections between all the blocks. And this is also a key driver for low-cost optical interconnect technology, high bandwidth technology. Looking at this very generic schematic of a data storage system, you would have disk drives. They could be hard disk drives, they could be solid-state drives. You would have a controller board. It could be a storage switch, or it could be a server. And you would have a power supply and a mid-plane, or in some cases a backplane. And what we're seeing increasingly is the trend in the protocols is we're seeing an increase in the speed of data that you're sending across the high-speed copper traces. This is a snapshot of the PCB, and you're also seeing traces getting closer together. You're seeing more and more traces, more and more I/O being introduced into the system, which means you have more channels and you have to cram them together. And this results in an exponential increase in what we call bandwidth density, which is increase in channel density times increase in channel bandwidth. One of the many fundamental problems we have to address is crosstalk. As you increase the signal frequency along a copper trace, you increase its interference with adjacent channels, and it interferes capacitively or inductively. Effectively, it's like an antenna in some ways. So in order to mitigate this, you have to move the channels further apart to within a new threshold. And the higher the speed of signal you send across it, the further apart you have to move the channels. And this means you have to increase the number of layers, because you're moving the same channels onto additional layers if you're not increasing the board area. Another important loss driver, and the most important loss factor, is dielectric loss. And this is where signal energy radiates out into the dielectric. And this is a big problem. In order to mitigate this, you have to really at the electrical signal source, you have to really ramp up the signal to take into account that it's going to dissipate quite rapidly. And the higher the speed again, the more rapidly it dissipates. So this means you have to keep trace lengths at a minimum, you have to increase signal power, you have to use special expensive dielectric materials, and you use signal conditioning circuitry, such as preemphasis and equalizers. Another second-order effect is called skin effect, and this is where, as you increase the signal frequency, the charge carriers, the electrons, tend to squeeze along the outer trace, the skin of the trace. And again, the higher the signal frequency, the more tightly they squeeze along the trace. And the result of this is that the effective cross-section of the trace becomes dramatically reduced. So as you increase frequency, you see a reduction. You see a reduction in what's called skin depth. Skin depth is the measure of the charge concentration from the surface. As you decrease skin depth with increased signal frequency, you see this increase in resistance, and so you have resistive losses. Signal skew is something very important because most high-speed electronic transmission lines are based on what are known as differential pairs. They don't send the signal along one trace, they send the signal along one trace and then the complement of the signal along the other trace, and they send it to a subtractor. And that way you subtract the noise and you increase the signal-to-noise ratio significantly. So this is a preferred method of transmission lines. But it means that you have to exactly match the length of these two traces always. If you don't exactly match them, this is an exaggeration, but if you don't exactly match them, you get a degradation of the signal. This means you have to match them on the PCB, you have to match them on any connectors that you're using, which adds cost, and there is always some skew introduced. And the result of this, all these attempts to mitigate these different effects, is that you're slowly seeing an exponential increase in cost on the copper side. Just to explain, this little diagram here is called an eye diagram, and it's basically a measure of how clean the signal is. The more open the eye is, the thinner these lines, the cleaner the signal is. But these different forms of deterioration make the eye blurrier and closes up and reduces the amplitude until you get something which is unrecoverable. Now, how can optics help? Well, let's compare the cross-section of one electrical signal channel. This is a differential pair again. First of all, we can send data further. We can achieve much higher densities. This is using a standard 250 micron channel displacement between optical channels. So at least 18 times the number of channels in the same cross-section for a multi-layer optical board. You can increase the link bandwidth through other methods, such as using wavelength division multiplexing or higher level modulation. There are lots of different ways in which you can increase the link bandwidth of a single optical channel. And you can create advanced passive and active structures like MMIs if you're using single mode waveguides, and all integrated into the board if you wanted. But usually it's integrated onto the photonic chip. And finally, you don't have the problem of RFI and EMI from the electronic trace. You do have a problem of optical crosstalk, but that's a different problem and more easily controlled. So, just as an example of the increase in density, this is a board that was developed on the SEPINET project, which was one of the projects we worked in. In fact, Lars Brusberg is giving a talk tomorrow about these technologies. It's based on glass waveguides. We take a snapshot of here. These are windows. The glass waveguides are here, but you can't see them. Behind it, I've put a normal board with normal differential traces, and this is the distance to allow, say, 10 gig signals. So I've highlighted here a group of 12 glass waveguides, and that's the space it occupies. It occupies the space of one differential pair, so you could fit far more in. So that's an example of the density improvements you have. And if you wanted, you could have a continuous. You could have glass waveguides just there continuously. So huge density advantages. So another key advantage is that the idea is we reduce power consumption. I mentioned before you have to ramp a signal up to overcome the various loss mechanisms in copper. In optics, yes, you do have loss mechanisms, and yes, you do need the additional active circuitry to convert the electronic signal to optics. But the loss mechanisms are more easily controlled on the channel, and if you put the optical signal driver, the transceiver, very close to the signal source, you don't need to ramp up the signal at all. You can use a very weak electrical signal to give you the optical pulse. And as you'll see from the talks, with further and further integration, we are reaching the point whereby we see an actual advantage in power consumption if you use optics. It seems counterintuitive because you're adding a transceiver in the link, but it's not. And material reduction. This is a fact. Because of the density advantages, you are reducing the number of layers in the PCB, and you can reduce the area. And based on a model of one of our systems, we've seen a 60% reduction in PCB material if we were to deploy the optical technologies. It's different depending on what your application is. Migration of optical interconnect. We return to this diagram of a generic data storage system. What we've seen for the last over a decade is edge board transceivers. SFPs, XFPs, and these Zen packs from previously. And there are always transceivers which sit on the edge of the card. So wherever your electrical signal source is, it could be in the middle of here, it's sending the electrical signal all the way to the edge of the card, and then the conversion from the blue to the yellow is the conversion from electronics to optics. And then it goes out with a fiber somewhere. What we're seeing over the past few years is optical midboard transceivers. Transceivers such as, in this case, I'm showing the Finisar BOA transceiver. These are it's the same technology, but it's just you put it in the middle of the board. You can put it very close to the electrical signal source and thus minimize the electrical signal trace length. And here you have an optical channel. It could be embedded in the board, or it could be a fiber, and it goes to, in this case, to a backplane connector. But it'll probably be more commonly seen that we'll have optics going to the front face here. So now you won't have an active device, you will have a passive device which achieves far, far greater density. And here you have just a very short electrical link, which is very nice. And is one step towards complete integration where you'd have the transceiver technology in the CMOS itself, which is something that's being discussed. And this lends itself to embedded copper and optical architectures. In this case, if we look at the PCB, you will have, you'll still need PCBs with copper layers for electrical power distribution. That will probably not change at all. And you'll need copper traces for low-speed signal distribution. But you would have optical layers. They could be fiber optic. They could be optical waveguides of polymer or glass. And these layers would carry very high-speed traffic. All the high-speed, high-density traffic could be conveyed by one layer. Some examples of this are, this is a fiber optic flex plane, which I'll talk about later on. It's part of our optically enabled data storage platform. This is a plane we developed a long time ago, 7, 8 years ago. It has a polymer waveguide. It was developed by IBM Zurich and Varioprint. Here you see an illuminated waveguide. And this is the board I showed earlier. This is developed from the SEPUNET project by Fraunhofer, IZM, and ILFA. And this is glass waveguides. So these are examples. And the question we've been tackling for the last 15 years, which many of us are very familiar with, is where's the crossover point? Where is this point? What data rate does this point occur? It's difficult to say. Even now I can't say. The prevailing protocols, we're seeing InfiniBand, 26 gig, around 2015, 2014. SAS, which is a data storage protocol, is moving to 24 gig in 2016, and PCI Express to 16 gig. These are important trends. Is the crossover at 25 gig? We believe so, but it depends on what your system is, what your application is. The crossover point could be now, if you have a higher performance application, or it could be later on if you have a lower tier application. So it can't be simplified in that way. One thing that people commonly believe is that the practical issues of converting an electrical signal to an optical signal are just you put a transceiver in and that's it. But no, there are protocol implications as well. I use an example here of SAS, Serial Attached SCSI, which is the data storage protocol. In the legacy systems, SAS has something called out-of-band signaling, and this is where on the main signal line, in order to talk to other SAS devices such as disk drives, there's a mode, a management mode, in which it inserts idles into the pattern. And the length of these idles is itself a command sequence, and it gives simple commands to the drives. Now, conveying this directly optically would be difficult because you need additional circuitry to avoid chatter, because the length of the idles must be preserved. So recently we saw a modification of this called optical OOB, whereas instead of the idles, they insert primitives. So that is to say they insert control characters, so you always see a modulation. So now you can set it optically. A couple of years ago, we developed the first optically or partially optically enabled data storage system, and we call this Lightning Valley. And this was a joint demonstration with Finisar, Hubazuna, and Varioptics, another side. And the principle was this. We didn't worry about the drives, which are usually on this side, but we just conveyed high-speed signals from expander, which is a type of switch, through a transceiver, through a polymer waveguide flex, through another polymer waveguide flex, and onto another board, and we just sent data from one control board to the other, and we sent a video stream in this case. This is another view of a schematic view of the system as it looked internally. And what we did is we demonstrated this at ECOC in 2012, quite a while ago. And we were streaming video data through it, uncorrupted, through the two boards. So that was a partially implemented optical platform. We weren't talking to the disk drives, which is the important part. So we then worked on developing a fully enabled optical platform, which we call Thunder Valley. And we developed as part of this is what we call a 2U24, which means it's 2U high and services 24 drives. It's a type of data storage enclosure. And inside it looks similar. You have two controller cards, which are switches again, but on the other side you have disk drives. And now this time we want the expanders to talk to the disk drives, which is normally what they do anyway. So they take data from the outside, they switch it, and they read and write to the disk drives with high-speed data. In order to do this, we had to develop more technologies. This is a view of the system with a controller card, and here you can see two optical transceivers. These are Finisar BOA transceivers. And here's another view of it, a close-up view. You have the expander, the transceivers, and a fiber ribbon, which comes to this pluggable backplane connector. And this is a commercial backplane connector. And here you see a fiber ribbon, fiber flex ribbon, which was deployed on the midplane. And this was actually developed by T Connectivity. Here's a front view. Apologies, this is a bit of a photo gallery from now on, so don't worry, I won't be talking long. I'll just be showing you the photos. This is 192 optical fibers in the flex plane. There are two parts, and they and you bolted them onto the board. It's nice to bolt them on rather than to glue them on because it's easy to replace and it makes no functional difference. And here's a view of it assembled inside the enclosure. We achieved the tightest in-plane bend radius of 5 millimeters here, and that gave us a great routing flexibility. And on the other side of the drive, we developed these proprietary receptacles. And these are optical receptacles. The empty ferrules from the flex plane came through the board and sat within these shuttered receptacles. And here's a front view of the real thing versus the schematic. And these receptacles were part of a connector system we developed. In order to talk to the disk drive, we needed to develop an interface card effectively. And this had a low-cost optical transceiver with fibers and a connector system that we developed. It was a pluggable compliant connector system with its own shutter. So if you have a front view of this connector, the shutter opens up as you engage it. It's designed to support an empty ferrule or an empty ferrule-sized thing. So, and this is the receptacle. This would be what would be sitting on the midplane. You have an internal spring for over travel, which you always need, and it's very easy to insert a clip onto the board. You clip it on and latches stop it from coming off again, but it still floats. And here's a view of the board actually inserted. So this is a hard disk drive, and this is the connector connecting into the midplane, into the flex plane. And here you see the backplane receptacles again. Now, how do we measure the performance of a data storage system? Well, this is one of the techniques we used. You send read and writes to the disk drives from the expander, and you measure the data transfer, the error-free data transfer. And what you get is a profile like this. And this is because they sweep the block sizes from smaller block sizes to larger and larger block sizes. And so this is the trend you would expect in a normal, traditional data storage system. And indeed, this is the optical trend we're getting, which is very comparable to the copper trend. So this tells us that putting the optics in makes it perform just as well as the copper. Well, that's great, but does that justify the additional cost? No, it doesn't. So what can we do to make it, what benefits of optics can we exploit that copper can't do? Well, let's look at disaggregation. We take this optical system, and then we insert a 50-meter fiber link in between it. So effectively, you're taking the disk drives and the control switch, and you're putting them on other sides of the room. So it could be on another side of the data center. And then we compare the performance again. And the performance is identical in both cases. And this is great because this is not possible in copper. You would always need optics for this at these speeds. The speeds are 6 gigabits per second. And this is a technology, an internal technology demonstration of the system. Slightly modified with Windows so you can see the things, but that was the first of its kind to show that it can be done. But our challenge now is how do you do so commercially, in a commercially viable way? How do you do so affordably? So we are actively engaging with partners across Europe and across the world in different collaborations. I'll talk about a few of these collaborations. Foxtrot is the major collaboration we're in now. OPCB was a historical collaboration which included the development of polymer waveguides and a new transceiver and connector. Starlight was a precursor to that, where we were really developing new ways to assemble cheaply connectors onto the PCB, optical PCB. HD Pug and SEPUnet. And these were funded through things like the Technology Strategy Board, which is a UK funding body, and FP7, and hopefully Horizon 2020 in the coming years. And this is a snapshot of our major collaborative partners over the years. So here we have the industrial partners, and here we have the research institutes and universities, some of them. So SEPUnet was an FP7 type project. It actually was a Piano Plus project with these partners, Fraunhofer, ILFA, Konjunkvis, and Teropta. And the principle here was to develop a method of making optical PCBs with glass waveguides and develop an ecosystem around it. So we developed connectors, and Fraunhofer developed glass waveguide technology. ILFA laminated the glass waveguide into a full PCB, and we ended up with a full technology demonstration with connectors, pluggable connectors, glass waveguides, and that's the first time that has been done. And here's the snapshot again. You can just about, I don't know if it's good enough, but you can just about see a thin red line here, and that's one of the waveguides illuminated with 650 nanometer light. So if you want to see this demonstrated, it was already demonstrated in Photonics West and Laser Optics in Berlin, but the next demonstration of this will be in ECOC in Cannes, and Anritsu will actually be taking one of these demo platforms, and they'll be sending data through it. And then after that, Fraunhofer will IZM, not Anritsu, Fraunhofer IZM will be demonstrating in Photonics West. So ECOC will be Anritsu, and Photonics West will be Fraunhofer. And the Foxtrot project, you've heard a lot about this, and you'll hear a lot about this later, so I won't go into it, but basically you're developing a whole ecosystem for optical interconnects at different levels in the data center. Board-to-board, fiber-to-board, on-chip, and chip-to-board solutions. HD Pug is another program. It's an open industrial collaboration, a US one. And there we're collaborating with lots of US companies who are directly looking at polymer waveguide fabrication and comparing it with high-speed copper transmission with different copper materials. That's a very interesting project. So in conclusion, we are seeing exponentially increasing bandwidth densities approaching the limits of system technologies in our design capabilities. And we've demonstrated the first optically interconnected data storage platforms in the world. Now we're working hard to see how to commercially validate them. And we are engaged in intensive research and development to develop the next generation of embedded optical interconnects. That's my talk. Actually, latency is an issue. There is, I showed 50 meter, but for something like SAS, you have something called time of flight. So we think optics is very fast, but actually it's two-thirds, it's the speed of light in a vacuum. And we don't believe you can send SAS further than 100 meters. So for the SAS protocol, we know, you shouldn't be able to send it further than 100 meters over fiber, because latency is critical for it. But there are new ideas being put forward for converged Ethernet in databases and lossless Ethernet, which might relax the requirements on latency, because that is recognized as an issue. And if we're going to move to flexible optical data centers, which are very large, we have to address it, because time of flight will be a constraint. Right.
one is going to be ahead of the other in the future?
We don't know. It could be both. I don't see. We work with all three major ones: the fiber optics, the polymer waveguides, and the glass waveguides. And for us, each one of those technologies has a place. There won't be a winner or loser because there's so many different types of interconnect, so many different tiers of interconnect. You could have, in my opinion, very short reach interconnect, optical, maybe on the same board between chip to chip. I personally think polymer would be the best contender for that because it's cheap and you don't have to worry too much about signal integrity, even though there are advances in polymer waveguide fabrication with graded index polymers. Glass, and it's ideal for 850. For medium reach, glass waveguides are very suitable because they're more compatible with fibers, so you can connect directly to the outside network to multimodal, single mode glass fibers, so you can have a seamless transition from the network into a system. And also you can have the same can be said for long reach. So single mode glass waveguides would be ideal for longer reach things, and a system could embed erbium doped amplifiers or something, and you can even have many different types of interconnect in the same system and same board. So. We can't cool down the systems. The data center operational temperatures are something we have to live with. But characterizing things like polymer waveguides, glass waveguides in different temperatures, that's ongoing. It's part of the Foxtrot project and other projects. So we age it, we cycle it. In the past, a long time ago, polymer waveguides were controversial because the materials tended to age very, very badly and very rapidly. Materials have advanced incredibly since then, the polymer waveguide materials. So we don't see the yellowing that we saw, 10 years ago. But intensive environmental testing on these new materials show very positive results. 85 for 5,000 hours. We're seeing no change at all in transmissivity. What did I go over, or was I under?
No, I think it was just about okay.
Oh, good. I was worried I was
Okay, thank you very much. So, our next speaker is Bert-Jan Offrein from IBM. He will talk to us about optical interconnects for energy-efficient data centers.
Thank you, Dimitris. Yes.
It's in there, okay? Is it?
It was in. I copied it yesterday. Where's that?
It's in the upper. Go up one.
Ah, okay.
Oh, okay. Yep.
Oh, here. Very good. Thank you. Okay, good morning. I will continue the presentation that I started yesterday and focus on energy-efficient data centers and what are ways to get to energy-efficient data centers and also to, say, a low-cost and highly efficient integration of photonics. So, as an overview, I will talk about the status of optical interconnects and computing systems, and I will use that to clarify what the benefits are, but also show you what the challenges are in integrating photonics. Then trends, and I will give you several examples that we've been working on in IBM research, also with partners, for board level, electro-optical links, also polymeric waveguides, and then related to silicon photonics, also ways how we would be able potentially to low-cost interconnect a fiber to silicon photonics chips, and in the end distribute single-mode signals across the board. And then finally I will conclude. So please, if you have a question also during my presentation, do not hesitate to interrupt me. Yesterday I already showed this slide indicating the performance increase in supercomputing systems with a factor of 10 every 4 years. So 3 orders of magnitude every 10 years, which means that we have to improve, say, all aspects of the system, the memory, the computing, the processor power, the storage, as well as all the interconnects within the system at all levels. And what I also discussed already yesterday is that, at least for computing, the main driver is at the moment density. Energy efficiency is becoming more and more important as well. But today what you see is that optics is applied if electronics is not able to do it anymore. And in the examples I will show you, it's really based on the density. That's mainly the challenge. So I want to come back to this as well, where to position the transceiver. Yesterday already and also this morning as active optical cables at the board edge. I will go quickly here, which has great advantages because we don't have to change the system itself. But we have the challenge that still the electrical signal has to travel through here all these several interfaces and this long distance to the edge. So it makes sense to bring the optics closer to the point where you generate the signal, closer to the processor on the board. But still, if you are here, it's important to realize that the interconnect density that you have, just the distance between the electrical connections at the board, is roughly something like 1 millimeter. So if you compare that to the interconnect density here at the processor package, on top, here it's about 200 micrometer or less interconnect pitch. So because it's a two-dimensional interconnect that you make, you have a tremendous interconnect density improvement if you go from the board to the processor package. In fact, this carrier substrate is more acting like a kind of fan-out of the interconnect. So you really win if you're able to bring the optics onto the processor package, because your electrical signals don't have to travel through these interfaces. You have a much shorter distance, and you win because the interconnect density is much, much higher. And for optical transceivers, what is limiting the size of the optical transceiver is the ability to get all the signals electrically in and out. That is determining the size. It's not the optics, it's really the electrical interconnect. So that's what you're able to minimize if you go onto the processor package. And in the end, fully integration with the processor itself into the silicon. But it's clear, all the changes have to go step by step. I think that's something we see very clearly, also in optical printed circuit board technology. In the past, we've been doing a lot of, there's been a lot of talking about, say, optical backplane technology when you were talking about optical printed circuit boards. I think where we see these kind of technologies being applied is not in first instance, say, over the long distance, but it's really over short distances. And it's the same, say, at system level. In order to increase, insert optics overall, we are going this path from insertion at the edge, where you can keep the system as itself electrical, and step by step have a closer integration. So I added this picture, but yesterday already there was quite some discussion. But what I want to make clear is what does this active cable look like, and what does it mean also from, say, a signaling and mechanical perspective to integrate these active optical cables. You see here an example where the nice thing is you have an electrical connector that goes into the system. So in fact, the good thing is here you can either attach an electrical cable or an active optical cable. The interface is exactly the same. So depending on the distance you have to go, when it's a long distance you take an optical cable, and when it's a shorter distance you take an electrical cable. This is how this looks with all the active optical elements integrated here into the connector housing. But on the board, you have also quite some additional components that are required. Clearly, you have to be able to get the electrical signals out of the board into the housing, with here these kind of connectors. This is a picture from Molex. You need the mechanical assembly to insert the active optical cable housing, and then you have all kinds of flavors. But you see there is, say, quite some, also here, again, electrical interfaces that need to be inserted. Here you have a lot of components in the transceiver itself. So there is quite some effort required in order to do so. And this is not less, looking at this example, which is a supercomputing system that IBM brought out in 2011 in order to, say, advance the overall performance. Now the optics is really mounted at the processor package, onto the processor package. And as I indicated already, what's done here is that you take this carrier substrate on which the processor is soldered, and you increase its size in order to make some space for the optical transceivers. And in this case, these are Avago micropods. They are 12 times 10 gigabit per second, multi-mode, VCSEL-based transceivers. So each transceiver has a bandwidth of 120 gigabit per second. And we have increased here this carrier substrate to host 56 of these transceivers. So 56 times 120 gigabit per second. It's about 6 terabits per second that we are able to take off optically using these transceivers. So it's 6 terabits per package, and we have 8 of these packages onto one board. So it's 8 times 6 terabits per second. That is additional I/O that is being transferred over this board using fiber cables. This is a tremendous bandwidth. This is a tremendous bandwidth that you're able to handle with the optics. And this is what I mentioned before. This is an example where you just would not be able to handle all this data electrically here through the board. So it really shows the capability of photonics to massively increase the bandwidth. And in this system, what you see is, say, we have here this backplane, we have several of these boards in one rack, and then there are multiple of these racks. All communication that's going off the board to other boards in the same rack or to other racks is all optical. Only communication within the board, from this processor here to memory to another processor, only that is electrical. So great. Optics is really helping us here. But let's have a closer look. What does it mean from an assembly perspective and from the number of components? If you just have an electrical system, what do you do? How do you assemble this system? You take the silicon chip, the processor, you solder it onto a carrier substrate, and you attach it onto the board. That's it. Now, in addition, these transceivers have to be built, and each transceiver contains also a little substrate, a driver, laser array, some mechanics, some optical components, lenses, an optical connector. So quite some elements. These were made by Avago. So the handling of this is not something we see as a system integrator at IBM. But what we do see is that we have to take, in addition to, say, soldering down now just the processor, we have to take 56 of these elements and mount them down onto this carrier substrate. And that's not all. Then all these fiber cables need to be attached. And you need to make sure that you attach the right fiber cable to the right transceiver here and also here at the edge. Now these transceivers, as I said, they have 12 fibers. So you have one connector, one ribbon with 12 fibers, so that's one attach. And then here at the edge, you have connectors of 4 by 12. So you have 48 fibers that you attach with one connection. But still, the overall system contains 2 million fibers. So it's a tremendous amount of manual attachments that you have to do. So it's a tremendous overhead, tremendous additional effort you have to do just to integrate the photonics. And this is something that is justifiable for a high-end system that is fully tuned to performance, but it's not justified for a standard system, mid-range, where cost performance is extremely important. So we are missing some basic things in in photonics that we have in electronics. Looking back, I mean, this is how electronics used to look. A lot of individual components connected through wires. And what's very important to realize is that today's state of computing is possible because of integration. That's clear. But when we think of integration, we always think of the silicon. But it's much more than the silicon. It's also the printed circuit board technology that enables massive interconnect without making, say, many individual wire connections. But it also enables, and that's also essential, it enables a massive connectivity in just one assembly step. If you take a processor package with thousands of pins and you plug it onto the board, you make thousands of connections at once. In photonics, that doesn't exist. And that gives the overhead in the assembly that we have to struggle with. So that's something that needs to be tackled. And that's why I believe these optical printed circuit boards are really a very important part of being able to go this path. Because, let's see, what I wrote here, for example, they are, say, similar to what we have in electronics, the counterpart combining electrical and optical signaling, and they would, in principle, allow the mating of numerous optical interfaces in just one assembly step. They provide both electrical and optical signal routing, and they allow close integration. And last part, based on the previous example, very important, you are able to avoid this massive cable handling. So, two examples here, one with embedded waveguides. I won't go in much more detail here. I will go in more detail into this one, where we have, say, two processor-like packages with optics that are communicating over waveguides on a printed circuit board. I will show you more on that. But first, a few words on the optical printed circuit board. We have put a strong focus on these polymer waveguides. And how are they made? We have a first lower cladding, and the materials we are using are all UV curable. So we bring on a first lower layer. In the materials we work with are liquid when we put them on. Then we cure them with UV light, a flood exposure for the cladding. Then the second layer is put on top with a little bit higher refractive index to enable guiding, and there we only expose where we want to have these waveguides, and we expose either through a mask or by direct laser writing. Then the non-exposed material is washed away, and finally the upper cladding is deposited. And here you see some examples of, say, multi-mode waveguides, size between 30 and 50 micrometer. As mentioned before, say, the reliability and also the processing of these waveguides has been a challenge for quite a while. We have a very intense collaboration with Dow Corning. They make silicones, and so we have a silicone-based waveguide material. And here we have achieved, say, tremendous progress, I believe, in terms of, say, processing. What we currently do is that we process these waveguides on very thin, flexible sheets of polyimide, because polyimide is a very stable material and flexible. We can process these waveguides, and one of the big advancements is that the material that we have established here with Dow Corning is extremely flexible in itself. It also has a very because it's so flexible, the waveguide sheets that we obtain do not curl, because the material in itself is relatively soft. Very low propagation loss. Normally we achieve 3 dB per meter, 0.03 dB per centimeter. Very important, it's compatible with solder reflow processing. So when we integrate these waveguides into a system, and you, in the end, to finalize the assembly, you have to go through a solder reflow to attach the chips, temperatures up to 280 degrees C. This is pretty critical for these kind of materials, but the silicones are able to withstand this. The same holds for, say, damp heat testing, where you have a very humid environment at an elevated temperature, 85% humidity, 85 degrees C. Also, say, several thousand hours is no issue at all. So with this, we have made tremendous progress here. And I would come back to this picture, where we have, say, two of these processor packages optically connected. And this, I can show you the capability of the optical waveguides in terms of the simplified assembly. You see here this, say, processor-like package. The processor could be here, where this word optomodule is standing. Then a signal would go from the processor into this SLC, high-density organic laminate. It goes to a transceiver IC, which is an electrical chip. And then here in this example, we have a 3D stack where this OE is a driver array, photodetector array. We have a lens array. So this is a two-lens collimated beam approach. And then the signal is focused here onto a mirror, which is integrated into the polymer waveguide structure through laser ablation. And then we have, in this example, 16 channels in both directions at 10 or higher gigabit per second. So in this case, when we have assembled this, when we have attached the lens array, then just in one attach, we can make many electrical and optical connections at the same time. But still, what you see, it's clear, it's a hybrid solution. We have integrated the signal communication within the system, but still this processor package contains a silicon chip, the CPU, driver, amplifier, as well as some additional components, electro-optical components, and these lenses. To go one step further in terms of integration, we have a strong focus on silicon photonics. And as you know, silicon is transparent for wavelengths larger than 1 micrometer. And what we are establishing within IBM is a technology in which we integrate both electrical and optical functions in the silicon. You see here, say, the functionality in a silicon chip, where we have the drivers, we have the electro-optical modulators through carrier depletion, and we have a wavelength division multiplexer and demultiplexer. So this is one silicon chip. Here on the receive side, demultiplex, detect with a germanium photodiode and an amplifier. I won't go into too much detail here because of time, but again, if we have this integration of electrical and optical functions in the silicon, the question comes up again, how to integrate this into the system and where to integrate this. And what we see now is that, for example, here in this Molex Luxtera active optical cable, QSFP, the silicon chip is integrated into a standard housing. It's an active optical cable. And this is a great way to start the integration of silicon technology. It's clear you have to provide known, established interfaces in order to be able to handle this in the system. But on the other hand, for us as a system integrator, the assembly effort remains more or less the same. We do not really win that much. Hopefully we win in terms of, say, the cost, because it's, at least at high volumes, it's a silicon-based technology. Maybe we can have some larger bandwidth, increased functionality through wavelength division multiplexing. That means less fibers in the system and less cost in connectors. But still, from an assembly's perspective, there is still improvement possible. And where I see this potential is in going maybe a similar path as I showed you in this picture on the say onboard processor package to processor package links, is that instead of, say, assembling transceivers, what we want to do is assemble the chips themselves, overcome the transceiver as a whole. And the way how this could look in first instance is that we have this carrier substrate, we have the processor, silicon, but then in addition we have silicon chips, the silicon photonics chips, that are mounted directly as chip, not as a transceiver, but as a silicon photonics chip onto this carrier substrate. When we have this silicon as a chip, then we can really tap into the high density interconnect here by soldering it down. But the challenge is how to handle the optical signals, how to get the optical signals in and out of this of the silicon chip. Where here come the waveguides into play again. And in the Firefly project, EU project, as well as in collaboration with Dow Corning, we have established a single mode polymer waveguide technology at 1300 nanometer with a waveguide core size of 6 to 8 micrometer. And here I show you one example of how the optical coupling between the silicon chip and these polymer waveguides can work. The basis is that we want to rely as much as possible on assembly technologies that we know from electronics, so a flip chip attach. Here you see the silicon chip, here we have this carrier substrate, here is the electrical connection. This is this polymeric waveguide, and you see here how the silicon waveguide is directly attached to this polymer waveguide. And then we expect coupling, optical coupling of the signals from the polymer waveguide to the silicon and vice versa. Well, if you just do this attach, nothing will happen because the silicon has a much higher index than the polymer. The polymer has an index of about 1.51, the silicon of 3.4, so all the light remains in the silicon. That's what you see here. But if we now start to taper down the width of the silicon waveguide, similar as what Fabrice was talking about yesterday, then at some reduced width, the light is not just guided in the silicon anymore, but starts to be pushed into the polymer waveguide. And when the width of the silicon is narrow enough, is small enough, then all the optical power will be in the polymeric waveguide. And this is called adiabatic coupling, but because what you do is a slow adiabatic transition of the mode field from something that is completely confined in the silicon to something which is in the polymer. And we've done this experiment, not yet with the electronics, but just passively with the optics, where we made carrier substrate containing single mode waveguides. We have attached the silicon chip. We have done it in such a way that we have designed S-bands in the silicon, in the waveguides in the silicon photonics chip, such that we can see, you know, the polymeric waveguides just go straight on, and there is an S-band in the waveguides in the silicon photonics. So if light is not coupled to the silicon photonics, it will just go straight through the polymeric waveguide and come out at the same level. Whereas if it's coupled to the silicon and then coupled back to the polymer, it will be offset by one polymeric waveguide because it goes through this S-band. So this way we can measure how much light goes straight through and how much of the light is coupled over. And what we see here, measured for 1530 and 1570 nanometer, is that we can get pretty low losses. Here in this case, say lower than 1 dB insertion loss. What you also see is that as a function of the, say, displacement of the silicon waveguide compared to the polymeric waveguide, there's quite some tolerance, plus minus 2 micrometer, and the loss is not increasing that much. And that's simply caused by the fact that the silicon waveguide has a very small size, sub-micrometer, a width of 400 nanometer, whereas the polymer is much larger, as a size of 8 micrometer. So what's important here is that the silicon is somewhere on the polymer. It must not be exactly in the center, it can be a little bit offset. And the coupling still happens, that's what you see here. We have demonstrated coupling loss even lower than, say, this 0.8 that you see here, down to 0.2 dB. But we saw later that that happened for cases where we have pressed the silicon waveguide a little bit into the polymeric waveguide. We think that by, say, adapting the design of this taper, we will also will be able to have lower losses for cases where the silicon is nicely standing onto the polymer. So, as a kind of summary, we see the photonics moving onto the board, closer and closer to the processor. Integration, very important at all levels, at the transceiver level, from hybrid subassemblies to full integration into silicon, but also, say, at the system level, from active optical cables to chip level assembly. Higher bandwidth is very important, higher bandwidth per fiber to reduce the number of fibers, either through multi-level coding or wavelength division multiplexing. If we go this path, we will be able to have higher bandwidth density, improved power efficiency, and in the end, also lower cost. So, thank you for your attention. Yeah, so at the moment we focus at the wavelength of 1.3 micrometer, and the light source is probably, certainly in first instance, a DFB laser or a set of DFB lasers that is hybridly attached to the silicon chip. But for example, what Fabrice was talking about yesterday, full integration onto the chip, I think that's something that is of high interest in order to reduce, say, the cost of the laser itself, and also to reduce the cost of the integration and to get a higher flexibility in designing the position of the laser on the chip. So that's something I'm also certainly very, very much interested in.
I may follow up. So are people also considering using some long wavelength gallium arsenide devices? You can do like 1100 or maybe 1200 nanometers. How does the loss of the waveguide compare at like 1300 and at 1100?
Oh, I can't give you numbers, but I think you already, if you go towards 1100, you already clearly see the increase because you come closer to the band edge.
I have two questions. Information between polymer waveguide and silicon optical chip. One is addressing the question: how much is the size of the pitch size of the single mode waveguide you show?
The peak size?
Pitch.
The pitch is 50 micrometer. Because that's the pitch we have in the silicon. So it's 50 micrometer, and then, okay, that was the example that I showed, yes.
And the second one is for attaching silicon wire and polymer waveguide core, you need to remove the upper cladding to shape the core.
Yes.
How did you do that?
Okay. We didn't remove it. We just didn't apply it at all. So what's happening? We don't apply the cladding in the area where we want to do the attach. So we then also do, say, a local exposure of the cladding only here in the area where we do not attach. And then after we attach, we do an underfill of either cladding material or another material which is suitable to have good flow properties and good adhesion properties. Such that optically, in the end, it all looks like filled with cladding. No. What's important is that the silicon is nicely standing on the polymer, and then in the end, we want to fill also the surrounding with the cladding. That's no concern in terms of the loss.
Energy consumption will reach the same energy per bit as you would get with VCSELs. Like IBM did 1 milliwatt per gigabit per second on a VCSEL-based link. Can you do the same with a silicon photonics link?
So, I would say eventually, in principle, yes. Today, silicon photonics is clearly consuming more power because you have a separate laser. It's a CW laser. It has to be coupled into the silicon chip. Then you do the modulation, so in principle you throw away 50% of the light, and so you need the power of the laser, you need the power of the modulator, then you have some, say, additional losses in your optical signal path. So I think today, clearly, a VCSEL technology is the most power efficient over the distances you go with a VCSEL. In the longer run, I believe that, say, with the integration of the laser onto the silicon and maybe even with a direct modulation of the laser mounted on the silicon and going instead of, say, Mach-Zehnder modulators, maybe to ring modulators, you're able to massively also further improve the power efficiency of silicon photonics.
One of the slides you showed for the polymer waveguide, they showed the dimension is 32 by 32 microns. Is there a particular reason why you chose this specific dimension?
Yes. The 30 by 30 micrometer was done for this. Let me go there. Here. Was done for this demonstrator. Because here we have a pitch of the waveguides of 62.5 micrometer. So the waveguides are very close together. So we can't make the waveguide too large. So that's why we reduced it to the 35 micrometer. Yep.
Back to the SOI and polymer waveguide coupling. We have an issue of the matching between the intensity of SOI waveguide and the polymer waveguide because the distance between them are different.
Matching the intensity. Yeah, so we have to. That's right. In principle, you can bring the waveguides in the silicon much closer together than you can in the polymer because the polymer waveguides are larger. So you have to do the design such also in the silicon waveguides that you're able to match what you can reach in polymer waveguides. So we have the 50 micrometer, and that's working fine.
Could you go again on slide 18? There was this silicon chip attached on top.
Yep.
Can you comment on the alignment tolerances in lateral direction and how challenging it is to get that right?
So you mean in lateral direction, you mean in this direction, right?
No, in the direction
Ah.
in the board. Sorry.
Because, yeah, that's what I showed here. We have plus minus 2 micrometer without an issue. Because what's important is that the silicon waveguide is standing somewhere on the polymeric waveguide. And the polymeric waveguide has a size of, say, 8 by 8 micrometer, so a width of 8 micrometer. So we have, say, plus minus 4 as a maximum. And you see that in plus minus 2, there is not a large increase in the losses.
There are some alignment structures that like passive alignment structures that you put it in? Or
Yeah. So the way how the attach was done in this case is that we used a high accuracy flip chip bonder. But in parallel, we've also been looking into, say, mechanical alignment structures to be able to, say, to have a lower cost assembly. And what we found there is that if we insert mechanical alignment features, say some larger structures in the polymer and some V grooves, for example, in the silicon, that we can have an alignment tolerance of plus minus 10 micrometer, and still after the attach, we end up with plus minus 2 micrometer as we need for the optical. So 50 micrometer is no issue at all. We never tried really less, but I think in principle, say 25, I don't expect an issue there. With a waveguide size of 8 micrometer, I think that should certainly.
I guess you have a very strong incentive to go further
I don't know. You know what we use these waveguides for is, as you see it here, in order to bridge a short distance. You know, the big advantage I see in this whole concept is that we are able, with this short stretch of polymeric waveguide, to do a transition of the very small mode size in the silicon to something which is adapted to a fiber. So it's a short stretch, and then we couple to a fiber, as you see it here. So we do a transition from the 50 micrometer pitch to 250, and then we couple to a fiber. That's the first idea.
In this case, I acknowledge that it's not a big issue. In general, I'm talking if there is a very strong incentive in the optical community to structure very densely the polymer.
I think the density we are getting, even with 50 micrometer pitch, is already so tremendous. I mean, if you just have hundreds of waveguides at the 50 micrometer pitch, it's still only a few millimeters. So, yeah.
What is the temperature stability of this integration with polymer and SOI waveguide?
So, the polymeric waveguides, we have tested those. They are stable up to, say, solder reflow temperature. The overall assembly, the testing thereof, if we go to a temperature cycling and solder reflow and so on, is something we still have to do. But I think it's a very good question because clearly we have different CTEs of the silicon and of the substrate, certainly the polymer material. So it's something to be looking at.
If you're looking to higher order modulation formats like 16 QAM, would that be a good way to go for higher miniaturization? Since you need less light sources, less modulators, but you still have a higher bandwidth.
I think that's why I've added it here also in the end. Certainly, yes, that's a way to go because you make more efficient use of your components that you have available. Absolutely. But as discussed yesterday already, I mean, you have a challenge in terms of the sensitivity and the power that you have to receive. Okay.
Any more questions? Let's thank the speaker again.
Thank you.
And before the coffee break, I would like to call Tolga Tekin to talk to us about packaging and assembly for 3D Optochips.
Okay. Would you please remind me halftime? So, sorry. Would you please remind me the halftime? So we will be discussing now the packaging assembly issues. It's based on my lectures at TUB in photonics packaging and also design simulation and reliability of microsystem classes. So I'm with Technical University Berlin and Fraunhofer Institute for Reliability and Microintegration in Berlin again. So the briefly description of this part, I would like to provide the challenges, current solutions, future trends in terms of developments for practical photonic packaging or photonic component packaging. So the benefits will be at the end of this 1 hour. I hope you will be able to determine the critical issues involved in photonic packaging and development. Probably you will be appreciating also the optical design of components, considering the packaging aspects. It's hard to cover all the topics. Normally, I mean, I reduced these classes to short course. We took half a day. Now it's again shrinked to 1 hour. So trying to cover at least a couple of items. So intended audience, I do not expect that you have a lot of background in the case of packaging, but sure, you will have in photonics. So in terms of references, there are a lot of books you can refer to, most likely optoelectronic packaging, critical review, and it's more or less microsystem packaging type of stuff you can refer to. These are English resources and a lot of German ones. So if you like to have a more dense, let's say, review of packaging items, there we have, let's say, 120, again, references to papers. You can study in more detail the issues. So photonics is a term end of 60s. It gave us the definition, basically, it's a science of harnessing of light. We deal with a lot of issues, optics, physics, chemistry, nanotechnology, materials, electrical engineering. So it's an overlap of all fields. Packaging, again, the same. Having a view, roughly, photonic today applications, it covers ICT, industrial production, life sciences, lighting, security, design and manufacturing. And in Europe, we have this towards a bright future to Europe, within that agenda, the explanation of topics within the ICT. In the next period, basically, it's focusing transmission, optical data storage, optical signal processing, and there are some specific fields below. To my understanding, the selected future applications in terms of photonics will be covering biometrics, fiber to the home, USB 4 supercomputing, radio over fiber, and so on. So since a couple of years, we are working within several projects in that areas. So some examples of those now recently with Commander, also in radio over fiber type of stuff. So my favorite is basically high performance computing, where you have higher performance, higher parallelism, reduced power consumption, less heat dissipation, and so on. So probably towards a vision or a dream, all optical computing. Let's see. I don't know if I will be seeing those days, but probably you will. In terms of objectives related to photonic packaging, we do see different interfaces. First of all, packaging is a core technology to leverage the functions in the performance of micro and nanostructures in a system. In order to bring them into the application, the gap between component and environment has to be bridged by providing reliable interfaces. So the interfaces what one consider are thermal, wireless, optical, mechanical, electrical, fluidic ones. And those I will try to cover. I don't know if you heard about the ITRS. Who knows the ITRS? Heard about it? Please raise your hands. Only one? 4, 5, 6, 7. These are all senior ones, so no students. ITRS is basically International Technology Roadmap for Semiconductors. And more than 1,000 engineers, scientists contributing to that roadmap. And it deals with future technologies and providing basically the roadmap in terms of semiconductors. It's somehow also including the packaging of optoelectronics in a side, in a niche. So it's been told that the assembly and packaging is more or less a very specific function in terms of photonics, and there have been a couple of examples listed. So as you can see, it's not the main focus of the community, the packaging itself, even for such kind of roadmap. In the title of the talk or of the course, you have seen 3D and system in package. So 3D is basically people using 3D integration in different ways. So if you don't have enough space, you are going up and rising up. So in order to have a low footprint. In our case, we do it in another way or from another reason. So the main motivation is basically to deal with the physical limitations in terms of CMOS scaling. So what we see is basically technological frontiers between semiconductor technologies, packaging, system design are disappearing, the boundaries. So at the end of the day, one needs kind of coherent solution for the entire food chain. The main issue or the bottleneck in terms of electronics or electrical transmission, we have seen today also by Richard, is the critical length. So what are the problems or challenges, reflections, latency, attenuation, crosstalk? It's basically provides us the critical length in terms of electrical signal transmission. So what is the issue? If you have such a structure, we do have only electrical signals. In lower frequencies, there is not a problem. We can transmit for longer distances. But if we speed up, due to the discontinuities, we do have a lot of degradation of signal and distortion. So there is no way that we fulfill the transmission lengths, right? And going through the terms, 3D integration, system in package, or 2.5D, there is no real good explanation of such stuff, but ITRS again mentioned is defining system in package in such way, saying that it's a combination of active electronic components of different functionality, and it may have optics, MEMS, passives, and all that inside. What is 2.5D? 2.5D is kind of folding the 2D structure in a way that you get the third dimension, and it's basically at the end of the day, again 2D. System in package, there are a lot of challenges since it's new, as you see also in ITRS. There is no standardization, no clear definition of parameters for optimal technology selection, and we need new design methodologies in terms of that. In terms of vertical integration, now the components are distributed along the substrate. You can go in 2.5D and try to build a more dense packaging, or in the 3D. Nowadays we are in that area in vapor level packaging. In the future probably we will be having kind of molecular 3D integration kind of stuff in terms of vertical integration. The bottlenecks remains the same for the system in package. Again, if you use electrical signaling, lack of low latency, high bandwidth, and high density of chip interconnects. So the solution will be sure the photonics to overcome these issues. So, in other hand, we see also the converging of technologies, which is basically shaping the future of our society. In the last century, we had ICT technologies. In terms of new technologies, nanotechnologies coming up, so, and that will transform a lot of stuff. What we see is the foundry or generic solutions to provide the converging technologies. Also, generating packaging aspects should be the main focus. So again, going back to the interfaces, Basically, it's nothing new. Microsystem technologies, integration or packaging technologies provides basically the basics for photonic packaging. Microsystem has a general description. Let's say starting with thermal interface. But for what purposes we have thermal interfaces? For monitoring and sensing. There you can use thermistors. And it's basically, there are different types of thermistors, positive temperature coefficient thermistors, negative temperature coefficient ones. Two examples, AD590 and PT100. These are most likely used in systems. So we have also the thermal interface in terms of stabilization of the set temperature of the system. One should be considering cooling in a passive way or in an active way. In terms of passive way, we had our heat sinks, and in terms of active ones, parity elements. Going to electrical interfaces, the purpose is basically to provide the power supply to the system and, in general, the data signal transmission. We do have microstrip lines, coplanar lines, other tools like soldering, wire bonding, clip chipping. We do have a lot of connector types to deal with, PNC, SMA, V, K, W, and we have to deal in terms of the entire integration also with impedance matching. You probably already know that the connector types, I'm going through that slide. In terms of optical interfaces, what is the matter? Numerical aperture, near field, far field, fibers, lenses, tapers, coupling losses, insertion losses, reflections. It might be destructive or constructive. So slightly we are moving into the direction of coupling light to the chip. So the fiber to chip coupling, there are different ways to do so. One can use butt fibers, ball lenses, self-hook lenses, half spheres, grinded tapered fibers, and pulled fibers. So it's basically the way or the tools which we can use for coupling light. It's becoming interesting since you already heard you need kind of alignment tolerances of plus minus 1, 2 microns in terms of light. So there are different methods to do the alignment. One can use all the freedom in the 3-dimension and using the 6-axis or linear motion motors to align the fibers to such chips. We have piezo effects to do more precise coupling, and also parity effects to come up. So probably, have you seen such a nano-positioning system, or who have seen such another? So basically, there are a couple of commercial ones available in the market. That's kind of active alignment of fiber to the chip. So one can use also flip chip methodology in order to have passive alignment. But what we do is basically to have as also shown in Bert's slides, bringing the chip, flip it, and put it on the substrate. If you have some structures which are basically makes possible to align the entire structure, such as V-grooves or solder balls, you can have accurate alignment. So in terms of flip chipping, again, it's a study itself. There are different types of flip chip bonding, so I don't want to go into detail in that slide. In terms of self-alignment, beyond that case active alignment, you can basically use the entire flip chip methodology in order to bring the chip to the right position in the case of the soldering. There are different flip-flip techniques or anisotropic bonding processes available. That's more or less applies to MEMS types of packaging. So now moving to electrical small interconnects, wire bonding, there the idea is basically to electrical connect the semiconductor material to the substrate. So there we see basically different forms of wire bondings, ball wedge, wedge, and there is a differentiation between the energy form. We can use thermocompression bonding, ultrasonic bonding, or thermosonic bonding, and depending on the material which can be used for the wires, we have by definition thick wire bonding, thin wire bonding, ribbon bonding, fine pitch bonding, and high-speed bonding. So it's again becoming a lecture for itself, but showing you some examples, chip to board, in terms of wedge wire bonding. So it's a very low cost wiring material in that case, using aluminum silicon, and it's bonds at the room temperature. Here is the example of ball wedge bonding using thick golds. So one can have also very good RF interconnectivity here. So at the right hand side you see aluminum based thick wire wedge bonding type of stuff. So it's more or less for power modules. If we can also compare and go into the detail in terms of wire bonding, comparing their advantages, disadvantages. In terms of ball wedge, we see we can deal with very high speed compared to wedge bonding in terms of the bonding speed. And there are different materials which can be used. So in all the references you can study it in more detail. So boundary conditions to choose the right wire bonding processes. The main criteria are basically electrical, mechanical, thermal characteristics of the circuitry, and depending on the application, you choose the right material. In terms of its wire bonding process itself, we do have first of all a cleaning phase and the formation phase, and then the volume interaction. So it's basically kind of interdiffusion. There are a lot of aspects which are affecting the quality of wire bonding, and in terms of vibration characteristics, temperature influences, and substrates. So I don't want to go into detail. Probably the photonic part is becoming more interesting. You have to at least to have a sense or understanding what are the techniques behind the packaging. Here we see different surfaces, lead frame, thick layer, and printed circuit board type of stuff. All that surface topologies basically affecting the wire bonding quality also itself. Of course, the reliability, as mentioned, is a key point. People developed basically pulling tests or mechanism in order to test the entire reliability itself. We do have this pulling tests and shear tests to come up with the stabilities or reliability issues. These are interesting. So what do you think, which one of these figures shows us the best wire bonding connectivity, the quality of wire bond? In which case, in which figure is the best? This is one. Who thinks it's one? Is that third one? No. Fourth? Fifth? Sixth? Wow. In terms of flip chip, again, it's a wide range. We do have weldings, adhesive joining, soldering. One can use fluxless processes, flux-required processes. Some processes are involved with underfillers in order to provide the mechanical stability. Here you see some examples, basically, for X-ray pixel detectors. Very small pitch distances and more than 60,000 IOs one can realize on such a small area. It's becoming a science itself, the entire soldering processes. It's the transform of intermetal phases, so it requires some understanding in material sciences. Here we see an example of 3D camera module, flip-chipped and 3D integrated. Using as interposer, silicon interposer and glass carrier. One can expand the examples also in other fields such as lighting, LED, packaging, so it's a very dense connectivity. I said reliability. Reliability is a study itself. One should today we are dealing with micros, but it applies also to macroscopic structures. The damage in a arc dam. So, and I don't know, probably the younger ones do not remember this Challenger takeoff, but the senior ones, sure. Small causes, but a big impact at the end of the day. So the reliability is an interesting issue. We see failures in different dimensions and different areas. So, but in the study of reliability or thermal management, we have to understand what are the categories. First of all, we do have some early failures. It's basically within the production phase. Then we do have intrinsic failure and overload cases that defines the lifetime, more or less, of the product. And then we have the phase related to the aging. So that's basically the curve over the time and the failure rate. The overload is basically defining the aging. One can define critical load and the load itself. If the load is lower than the critical load, there is no failure. It's beyond that limit. It fails 100%. So people try to define or estimate the reliability issues, lifetime issues, and they came up with some failure distribution analysis. So in that example, we see Weibull distribution. It describes basically the mean time to failure in the midpoint. Potential failures, failure mechanism, these are very diverse. We do have issues coming from mechanics, thermics, electrical ones, radiations, chemistry, and there are also wear-out mechanism, again related to mechanical ones, thermal ones, electrical ones, and so on. So the motivation, especially in the photonics, here in that given example for harsh environment in the case of automotive, but it's similar to that. We do have several loads. First of all, the temperature, then some forces and humidity. Of course, in data center, we will not have humidity, but we will have the case of temperature. One can come up with simplified models and examples in terms of flip chipping. There's a chip and there's substrate flip chipped on that. If you change the temperature, with delta T due to the different CTEs, this CTE mismatch. They do extend in different lengths, so at the end of the temperature delta T, we will have the case that there will be some forces which will be acting at the interconnects. One can analyze it also in more sophisticated ways in using FEM models, the entire reliability issues. It's only the same type of topic, and it's basically. So we have roughly the half time. So should we speed up? Here you see basically again some examples in terms of where the failure can occur in terms of the reliability. The trend is basically, since we move in 3D integration and micro-nano packaging, in all ways we should consider within the design the reliability issues, and it's becoming a science itself. And if you further miniaturize and go smaller and smaller with dimensions, the only problem at the end of the day will be related to thermal issues probably. Heat conductivity, there are different ways to do so. Here, that slide shows basically different cooling concepts which could apply to, in general, microsystems. We do have air cooling, enhanced air cooling, liquid cool systems, refrigeration type of stuff for different type of devices. It can be implemented. Most likely for photonics, we do have active cooling, and we see basically in data center applications in such racks or growers from IBM, also liquid cooling. The cooling itself is becoming interesting since we have to deal with different mechanism of heat transfer itself. We do have heat conduction based heat transfer, convection type of radiation. So it's basically most likely we will not have in a very closed environment convection within air, but we will have heat conduction. One can also analyze the heat conductivity with very simple models. It's very similar to the analysis with what we have in electrical engineering. Basically, at the end of the day, one can come up with a very compact model which gives us basically the temperature difference relation to the thermal resistance and heat flux itself. The same equivalent circuitry models which we have in electrical engineering for analysis of such complex systems could be applied to those also series and parallel. In terms of heat conductivity, one can consider different materials. The best heat conductor is diamond. So, in very specific cases, one can use diamond since it's kind of expensive. But silicon is well used in microsystem integration and also in photonics integration, since it's kind of cheap and provides a good heat conductivity. Heat spreading, and let's move to some packaging examples, since we have some understanding in the metal tools which we can use in terms of packaging and assembly. Packaging became interesting after having the first, let's say, photonic integrated circuits, mid-90s. the first photonic integrated circuits came up based on indium phosphides, basically here in order to avoid the reflections at the facets tilt waveguides have been considered. That chip was designed in order to characterize it on a table. It was not designed for packaging. Since the angles are in across positions, it's not very intelligent for packaging. Later on, we modified those kind of chips in order to use some commercial available interconnects, such fiber arrays. In that case, of course, one can also consider kind of tilt waveguides, tilt facets, and tilt basically fiber array kind of stuff. Now, in this autumn school, you will hear a lot on silicon photonics. Basically, to my understanding, silicon photonics is not only for, let's say, some functionalities. One can use it also for packaging. It started in the 80s with microstructures. Since we have converging systems, one should the approach have been moved. Currently, the foundry solutions are there for multi-project wafers. The question is always the IP, the libraries, are those open or not? But in general, silicon photonics can be used also for as an interposer and for 3D integration, for system in package. I get in touch with silicon photonics early in EPICSnet projects, and due to the packaging issues, and through Helios and Platon, IFOS, Ramplas, and Foxtrot projects, we moved through those paths. So, in combination of silicon photonics, one should be always considering kind of optical PCBs based on glass or polymers. It's in general a compact microsystem type of stuff. There is a lot of roadmaps given by Intel, Oracle, IBM. So it's a very complex view. You'll see in next days also, probably seen yesterday also, the silicon photonics issues. In order to understand silicon photonics, one should probably step back and take a look what are the success stories by silicon photonics at least. We have the first success story in terms of microelectronics. So ICs, late 70s, VLSI circuitry and the entire integration driven by DARPA. It was easy to do so since every transistor was the same. The second success story in the generic approach is related to MEMS, again driven by DARPA. In the beginning of 90s, it became successful, and now we do have also a multi-project wafer type of stuff here. Going back to photonics, it's not only electrons, we do have also photons to deal with, so that means the structures are very diverse. There are passive components, active ones, different materials, compositions, different doping, and different wavelengths. Multi-project wafer type of stuff is hard to bring in a generic way. But Intel came up with such kind of building block. You have seen those parts, and some other companies are following this approach also. The packaging of silicon photonics becoming challenging nowadays, since historically we moved from microstructures to nano waveguides. In terms of micro waveguides, if we do basically bare end fire coupling with SMF28, we do have in the range of 3 dB loss. If we move to smaller dimensions, again, end-fire coupling, we do have a loss of 12 dB. In terms of nanostructures, 0.2 micron, we do nothing. End-fire coupling, we do have a coupling loss 20, 30 dB. So, people came up with the options of grating coupler. We have seen those. So it's basically out-of-plane coupling. It gives us the planar processing issues, but the button or the challenges are related to polarization dependence and wavelength dependence. We studied the alignment tolerances in terms of such grating couplers. Here the given example from IMEC, the grating coupler, 17 nanometer edge depth, and the periodic 25 periodic structures there. The measured alignment tolerances plus minus in the range of plus minus 2 dB. We do have, let's say, smaller than 1 dB loss. So that's pretty good. One can start to work with that using some commercial available fiber arrays. We studied further the entire coupling issues to such passive structures in order to align the fibers. There have been some shortcuts introduced within the entire structure to align basically the grating coupler A to H are shortcutted, so we have the entire path. But you know, the silicon photonics, there you have very good processing tolerances, but it does not apply to the environment, the packaging environment. There's some commercial available V grooves. They do have, by definition, also some failures within defined by the position of the fibers. So we studied those. Where is the coupling center? So there is a slight mismatch. Basically, if you use perfect aligned structures with some commercial ones, but it's basically within some alignment tolerances, and you can, at the end of the day, survive with a coupling loss in the range of 5 dB, which is better than compared to the case of 30 dB loss in terms of end-fire coupling by using such grating coupling. So the first examples within Europe in terms of silicon photonic packaging, here you see the silicon chip directly attached on the commercial available fiber array. And within that process, we do have basically a penalty, fiber coupling penalty in the range of 1 dB through all the 6 or 8 channels. That was the one passive chip, but not all the chips are pure passive. We do have also electrical interfaces. So that's the concept in order to basically bring some electro-optic soy chips to the environment. This again a generic packaging concept to support 32 IOs. That's in the beginning. One can extend it, sure. It's only the limitation is the availability of such commercial fiber arrays. You have seen probably also the inverted taper perf issues. One can bring the in-plane coupling in such way where we taper the silicon waveguides and basically bring it to some polymer structures, and then one can also etch by using MEMS technologies some big grooves and possibly align the entire fiber to the chip. Since we deal with packaging, and we thought it's necessary to have kind of design rules for packaging for silicon photonics. So at that time we came up within the EPICnet with some considerations in order to organize the structure in the multi-project wafers, basically define the area for optical ports, define the area for electrical ones, and so on. So using the well-known microsystem integration technology tools such as fiber pigtailing and flip chip and wire bonding issues, we came up with a list of design rules which should be considered within the silicon photonics chip design. So that have been implemented also in several projects. Here you see an example from Boom. It's a photodetector array combined with that kind of generic packaging concept for a tiny silicon chip, the fiber array itself, and the integration platform to bring the RF signals to the environment, and also the TIAs and all that stuff can be integrated on such packaging concept. Later on, you see basically here the challenge, or the, let's say, the disadvantage using vertical grating couplers in combination with the commercial available fiber arrays. Where we have high profile, we came up also with some low profile packaging concept where we basically turn the silicon chip, apply or put it on in the other way in the package to provide a low profile packaging concept. That's basically, this part was basically dealing with silicon photonics and its packaging, but silicon photonics as a, let's say, component within the optical or photonic system. One can consider also silicon photonics in case of packaging as a packaging platform. For that, it's only needed to combine low assembly and guiding issues coming up from silicon photonics. The fact is that system complexity and functionality is increasing, so since we need kind of seamless applications, the first step is that generic foundry, generic packaging concept. So in terms of generic packaging, silicon photonics itself can serve also for a generic packaging concept. So here, one can call it heterosilicon photonics or whatever it is. It's kind of integration platform combined with all this microelectronics, 3D integration stuff. Basically, the layers which came up from CMOS, we can additionally add a photonic layer within the objective, having optimum systems with huge throughput and better performance. It's basically again mix and match of different functionalities and integrated three-way. The simplest way could be kind of photonic interposer, optical interposer, combining the electrical interposer with photonic layer, and the entire microelectronics packaging know-how and integration know-how in 3D in general based on TSVs through silicon via technologies can be directly applied to such kind of interposer, which which can be used again as a packaging platform itself. We started to work on that kind of building blocks within the Pitwon project. It was basically addressing terabit silicon plasma regulatory. You will be hearing from that project probably in the next couple of days again and again. So there we have a silicon platform to integrate the entire functionalities and basically also plasmonics, some logic circuitries, some optical functionalities. So that was basically the first step towards the heterogeneous integration, then 3D integration itself. Again, that kind of stuff should be packaged, right? But it's, again, if you consider the entire interposer concept, it's always the case. Developed packaging. Now, going to such a heterogeneous integration platform and combining our micro integration or microsystem part of stuff, we are over the time. One should be considering the entire IOS interfaces, and one could be easily come up with different packaging concepts, but at the end of the day, or how to advance the packaging technologies for the future. So, to my understanding, packaging first of all determines the functionality and cost reliability of future systems. So there is no debate on it. But the system in package is one way, plus photonics, yes. We need always some generic solutions that requires modularity within the integration, and probably in that case I will be promoting silicon as a photonic component and also as an integration platform in an interposer case, since there we have the entire capability to come up with a smart support for the entire components which can be hosted on a given system. So probably we should stop here. I don't know if you have any questions. Yes. Since we are on time.
So, let us start in the new session. So this session includes now 2 speakers, and after that we stop for a lunch break. The next talk is coming from Duis from TE Connectivity, who will talk to us about active optical cable technologies.
Thank you, Nikos. Welcome, everybody. Today I'm representing TE Connectivity, the group in 's-Hertogenbosch out of the Netherlands, where we have been working out a design for an active optical cable. So I'm going to teach you a little bit more about an active optical cable, what's inside, and what we are doing to it, and also give a little bit of rationale around it. I think already quite some has been given, but maybe some points that I will elaborate more on. Maybe first a quick introduction of the company itself. So TE Connectivity is a big company, so it's about 13 billion of turnover. It's about 90,000 people working worldwide, and the group in the Netherlands is about 350 people. If you're looking to where are we located, it's briefly located all over the world. So it's 1/3 is in the US, 1/3 is in Europe, in EMEA region, and 1/3 is in Asia, including China. A few years ago, TE was not doing a lot of innovation, and it has been changing actually with the come of our new CTO, Mr. Rob Shaddock. So there was much more focus on innovation, which resulted in much more patents being submitted and granted. And now we're also recognized for the second year by Thomson Reuters in the top 100 most innovating companies. Maybe very quick, so it's not all about fiber optics what we're doing with this 13 billion. Would be nice for myself, but for sure we also have different business units. So it's about automotive, where we're doing a 5.5 billion, where also our group is actually working on a optical link within a car. Most of the people don't know that even in BMW 7 Series from 6 years ago, there were optical links inside that were supporting a bandwidth of 25 megabit a second. And actually last year it was upgraded to 150 megabit a second on a plastic optical fiber. So plastic optical fiber in automotive and data communication is existing there already. And for sure, the next generation will be focusing more towards a 1 gigabit link, which will be derived from the data communication field, which is actually very hot right now. For sure, you also have the aerospace industry and industrial industry, especially if you're looking now to robots, welding of cars, for example, or welding of parts of a plane. These robots actually are using very high currents, and you get, as we learned this morning, there's quite some EMI, so electrical radiation actually coming from welding machines, and people are actually looking for how can we get more data to this welding machine and vice versa, actually to do the inspection of all the components that are coming there. So also for optics, I think that's a very nice field where we can be much more active in than what we are today, since this field is really open for the EMI protection. Then there's the consumer area. Most of the people already have a high definition television, so that has been coming a few years ago as like a standard, but still you see the trend of televisions to grow bigger and bigger up to meters of diameter size. For sure also there we don't want to have big pixels that you're looking at. You want to go to finer grid sizes, finer spaces, so you're getting high definition recording, ultra high definition television, where also there the speeds are going up to tens of gigabits a second. The majority of the active components are now actually sold and used in data centers. So as you can see here, it's not only the data center that we are active in, but also telecommunication, enterprise networks and subsea. I'm going to show you a brief video, maybe to wake up everybody, like where is fiber used today? So it gives a brief glimpse.
Every day, the world counts on advanced fiber optic networks to make information instantly available. NTE connectivity is there, making critical fiber connections more reliable, faster, easier to manage. From the desktop to the data center, across networks and around the world. This is how fiber comes alive.
And as you can see, for sure, it's not alone fiber, it's fiber combined with electronics. So we also need all these wireless antennas for your mobile phones, that you can just dial numbers on your mobile phone and send emails. And then when it's reaching the pole, that's where it again goes to fiber optics. So here you actually see like where TE is active in. So we're active in the whole field, actually from the data center to the fiber distribution areas to actually the boats that are here. That are placing the fibers on the bottom of the ocean. So we have about 8 ships which are just putting these big cables over there. But also with events like the soccer event which is upcoming, there's a massive amount of data that needs to be transmitted. It's more than 25 gigabytes a second that's actually coming out of the soccer stadium, which people are generating by just recording the movies, the goals and whatever is ongoing in that area. So maybe as background, this image has been shown before already, I noticed. But when I joined the field of optics, so with TE connectivity, that was 12 years ago, these kind of images were shown a few years later, in 2005. And like everybody stated, okay, well, if 5 years from now we have optics in a computer, and probably 10 years from now the optics will run on the board of the computer. Well, nowadays, if I'm still looking at my home computer, it's not implemented there yet. We are just seeing it coming up in this high-performance computing area in the data centers. And for sure, Bert Offrein mentioned this morning already, you need to catch up with Moore's law. So you need a 3-digit improvement over the upcoming decennium. So that's for sure something where electronics so far has been doing a very good job in just improving what they have been doing already for a long time. So it seems that the target that we're trying to hit with optics is more or less like a moving target, and each time when we think we're there, it's just like, okay, the electronics guys come up with a new trick and it's still working. So for sure, when it will be implemented, or when it will be implemented on a mass scale, that's something that also for us is not completely clear, but for sure we are looking into it. As you can see from the bottom picture, first instance, telecommunications or glass fiber optics was all used for long distance communication. And over time you will see that we are going to like smaller distances, shorter distances, much more distances, which also require completely different assembly techniques. So today, if you're looking to fiber optics, a lot of the cable assemblies, for example, that's still manually terminated. But as soon as you're going to much higher volumes, like hundreds of millions of pieces a year, then for sure you would need to go for fully automated assembly and take out all the labor that's in. So for now, I'm going to elaborate a little bit more on the 100 and 400 gigabit active optical cables that we are manufacturing. So again, here this is used for data center applications. In the past, TE was mainly known for its upper products, like the passive interconnects, multi-fiber interconnects, also the casings where the transceivers needed to go in. But a few years ago, we did the acquisition of Zarlink out of Sweden. And that's actually bringing the optical components that we have on the bottom side, and with the integration of Zarlink completely within TE, we can deliver the complete solution from the case to the casing on the other side, and also help to guide on the electrical design. So what's critical for this active optical cables? It's the amount of gigabit per second per square millimeter. So how much bandwidth can you get out of 1 square millimeter? It was shown already that fibers do have a much higher density than what you would get at this moment with electronic traces. The power consumption, so here it's stated watt per gigabit per second, but actually it's milliwatt per gigabit a second, or even picojoule per bit. So people are using different terms to mention the same number. Then, of course, you have the cost. So what is the amount of dollars per gigabit per second that people are willing to pay for it? Since especially if you're looking to Moore's law, when it actually all started, each generation, or each 18 months, when you had a factor of 2 of improvement, the same was applying not only for the improvement, but also the cost was actually getting down with a factor of 2. And the power consumption was getting down. And that's something for optics where we also need to play an active role in, not only look like how can we get into this computer, but also how is this sustaining to the future, and are we really scaling with Moore's law. So here you can see an image of a CoolBit. So that's our integration platform. So on the bottom left side, I will show more pictures later on, where you can see a glass substrate with on top of that a driver and a VCSEL, and on the other side you see a photodetector and a transimpedance amplifier. And this is a building block which is used in all the active optical components that we're making at this moment. And for example, here you can see a midboard optic. So then instead of 4 channels transmit, 4 channels receive, we're using 12 channels transmit, 12 channels receive. So it's in a group of 12 instead of 4. And if you take 12 times 25 gigabit, you're ending up with a 300 gigabit module. The same is with the CDFP. I'm going to hand it around so you can see inside what's in there. And since it will take some time, I'm going to do it right now. So what's actually inside such a active optical cable? What I mentioned already is like we need to keep up with Moore's law. And if you're looking to VCSELs, the energy consumption of a VCSEL is about 20 milliwatts of energy. Whereas if you're looking to a total optical link, the link is consuming about 200 milliwatts of energy. So it means that more than 90% of the energy of an optical link is actually used in electronics and not in the optical field. So that means that if we want to be scalable with computing and with Moore's law, we need to keep track as well on the power consumption of the driver electronics and the transimpedance amplifier, which is actually converting the signals to the optical domain. So what we are doing is we have a group in Phoenix, Arizona, which is actually designing the electronics chips. So you can see here there's a CTLE in here, equalizer circuit. There's an amplifier in there, there's clock data recovery, and the driver, which is actually giving you the right current through the VCSEL. And then that's coupled to a multi-mode fiber in our case, since we're using 850 nanometer VCSEL technology. On the other side, you have a multi-mode fiber again coming in. You have a photodetector. For sure, for these high speeds, you have very small photodetectors to reduce the capacitance. You go to an amplifier, clock data recovery, and actually you're feeding the signal out again to the receive area. And this is just repeated for each channel that you're having. So if you're having 16 channels, you have 16 of these circuitries actually for building up the link. And to control all this, you have a microcontroller, which is actually setting the currents, the temperatures, to make sure that the signal, especially when you have high and low temperatures in data centers, to actually make sure that the bits are coming over at the right way. So here you get a glimpse of the wafer assembly. Since in the past it was mainly done on a PCB level with lots of active alignments. So that was actually quite a lot of cost, and you need to go to submicron alignments, and these machines are typically not very fast. So Tolga mentioned already before, we have flip chipping, and then with self-alignment, you can get self-alignment of components. So that's actually the technique that we're using over here to align the VCSELs with respect to a metal layout on a wafer. So here we're using 6-inch wafers. We are flip chipping down VCSELs, photodetectors, drivers, and limiting amplifiers. We are putting them through a solder bath, so typically 300 degrees C. It's called thin solder reflow, and then by the van der Waals force you will get the self-alignment of the chips. So when they are cooled down, we're actually getting a underfill underneath the VCSELs and the photodetectors, the drivers, and limiting amplifiers to make sure that also the components are remaining in place. Since just the soldering itself is not strong enough to maintain the reliability for all the tests that are coming or the requirements that you have in a data center. So here again you see a schematic of the transimpedance amplifier, the cool bit engine, and how it is built up. Note as well that, like also on the glass substrate, you can see here, there's quite a lot of ground planes. So it was mentioned already, EMI is critical. So you need to make sure that EMI is controlled, especially in the active component, where you have currents from the VCSEL, which are more than 1,000 times higher than the currents which are received by the transimpedance amplifier. So if you have a very small amount of energy leaking from the wires, which are going from the VCSEL driver to the VCSEL array, then for sure you will pick it up at the receive circuitry, and it will immediately end up in crosstalk, and therefore you reduce your bit error rate performance. If you're looking to the CDFP, for example, the technology that we're using, or the QSFP, we have these glass engines. We are soldering them onto a PCB. So that's again a soldering process. And what we typically do there is the PCB soldering at 260 degrees C. So that makes sure that the gold tin, for example, is not melting anymore, but the tin itself that you're using at 260 degrees C is melting, and therefore you get a good fixation of the Pyrex engine without desoldering the other components that you just put on the glass. After that, we are assembling a molded optics lens. So you can imagine already looking to the component that's going around. It's a pretty small component which already has like 12 V-grooves to actually place the fiber in. It has a 45-degree mirror facet, and on the bottom side you're also having 12 individual lenses. This all needs to be aligned. This all needs to be working over a large temperature range. So coefficient of thermal expansion and misalignment that you will be getting due to temperature, that's something where this lens is specifically designed for to really make a robust interface. Then we align the lens on top of the PCB, also with flip chipping technology. We are bonding it there in place, and then we can just put on the cables that are required. And for sure, we are typically doing it with 4 channels transmit, 4 channels receive. So for a 16-channel device, you just need 4 of these engines to be incorporated. What's the total advantage if you're looking to it? Since we heard already, like energy consumption, that's something which is critical. It's getting more critical over the years. What's happening to it if you're really looking into the detail for such a small component, how it affects the total system? If you're looking to a server where this is being used in, and we are saving 1 watt, if you're adding that up, you see for the DC-DC conversion that you're saving an additional 0.18 watts. Then from AC to DC, you're saving an additional 0.3 watts. Then you have the power distribution, adding that up with the UPS, the power device that makes sure that if the power goes down, that the computer will still run. Then you have the cooling, so the air conditioning units, they can be under-dimensioned by saving power. So in total, if you're just adding this all up, for each watt that you're saving on hardware level, you're saving an additional 2.84 watts in the total infrastructure. So the power consumption is not, the power saving is not really in the cable itself, but it's really in the infrastructure which is going around it. And please imagine, Bert Offrein mentioned already, for one processor that you have 12 channels times the 56 next to each other. So the 6 terabit link. Typically in data centers you have hundreds to thousands of these modules just sitting next to each other, communicating whole day and night. So briefly, our active optical cable. So we have a 100 gigabit solution. So it's in the past we had 40 gigabit. So that's the same technology, but then 4 times 10 gigabit. Now recently it's upgraded to 25 gigabit, which also stresses, of course, the whole electrical domain. So also the electrical customers from our side need to switch over to 25 gigabit, which typically means they need to switch over to completely different routing architectures, different PCBs. They need to go for different chipsets. And it's taking quite some time before everything is standardized. So typically we have here a few standards that we're compliant with, so the IEEE standard, the InfiniBand standard, which is actually depending on which data center or which computer architecture people are using. Quite recently we had a 400 gigabit active optical cable, and that's actually a multi-source agreement which we started. So we noticed that within standardization, that's great if you have like a roadmap that you can comply to, but sometimes you also have customers that actually want to get something specific and they have like a small customer base, they want to have second sourcing. So then typically it makes more sense to set up a multi-source agreement, so that at least with a few partners you agree this is what we're going to make, and then you're going to develop a standard around it. So the connector that's sent around, that's the 16 channel solution, and it can have a reach of 100 meters. And for sure, I mean, if you're looking to the density, each time also when we are coming up with like newer platforms, the density is something that we need to comply with. So here you can see that for a 16-channel device, we are only using 33% of the existing footprint if you would use the original dimensions. So if you're looking to this, we are nicely following with Moore's law in that respect with the scaling and the dimensions. The midboard optics, sorry, that is unreadable. I noticed later on that this font has been changed somehow. But here I have a nicer slide. So it's actually showing the build-up of this module. So you can see over here the complete module with a PCB and the engine. And here you can see this engine being mounted to an MT ferrule. So it's typically a 24-volt ferrule with 2 rows of 12 that is actually connected to the rest of the system. And then on top of that, of course, you can choose for a heatsink. So the heatsink can be either a air-cooled solution, but of course, depending on the architecture, it can also be liquid cooling, and then you can just have like one heatsink covering multiple of these devices. On the bottom side, we're actually using a BGA package, to make sure that we are having a good physical contact. So in the past we have been looking to alternative solutions as well, but the advantage for this is of course that you can replace it afterwards if something goes wrong or if the system is not working. So you don't need to throw away a complete blade, but you can just repair it where required. Also, it was mentioned this morning, I think by Richard, like, okay, the electrical links, that's something that are getting more complicated as well. So the CDFP and the QSFP, that's typically a connector which is the front I/O. So you have a long trace actually from the electronic chip to the side where you're connecting it to a fiber. And actually to overcome that, also we have this midboard optics, which you can place directly next to the ASIC. So here you see an example of an ASIC with multiple midboard optics around it, and then an optical fiber actually going to the front I/O. So this presses also for companies like TE more to how do we go for fiber routing and reduce the assembly. Well, we don't have optical PCBs yet, and we don't have the thin glass substrates yet that we can use to implement. But what we do have already is a fiber routing technology. So this is more like a double-sided tape or a sticky tape where we are putting a fiber on. We are laminating that with a coating. The coating is cured, and then you're ending up with a circuitry. So with this technology, you can route to each individual ASIC where it's required inside a computer. And Richard already gave a nice example of where it was really implemented into a hard disk drive solution. Maybe also good to know is that the technology, that the fiber routing technology is for sure not limited to the waveguide dimension that people want to use. So typically for the thin glass technology or for the polymer waveguide boards, you need to have a complete process developed for each waveguide that you want to manufacture, whether it's single mode, multi-mode, small numerical aperture, high numerical aperture. Whereas this, it's really like you're buying a fiber, which is already a well-established technology, and you can just put down that fiber onto the circuitry. So you can just use a bend-insensitive fiber, now that has been coming out, and also reduce the losses in very small bends and therefore make much more complex circuits itself. So this is again referring to like what is the actual output that you can get from the front I/O. If you would be using midboard optics, you're getting rid of big connectors on the front side, so you actually place them on the board, and typically that's an area where you have a little bit more space actually to have these modules, and you're freeing up the front I/O surface. So what you can see here on the right image is actually the amount of space that you would have if you would be using MPO interfaces instead of CDFP interfaces to make the interconnects. If you want to know more about the technology itself and also how we are making the VCSELs and the photodetectors and assemble them on a CoolBit, you should look at YouTube. If you just type in there CoolBit and TE, the movie will just pop up, and it's about a 7-minute video which is showing a glimpse of our factory that we have in Sweden. Thought it was too long to integrate it here. Now maybe going a little bit more upstream. So we have been talking about the data center itself. So data center is one part, but now you're seeing that data centers are getting bigger and bigger. Companies like Google are actually requesting active optical cables with lengths of 2 kilometers, and that's something that we cannot bridge with a multimode technology at this moment. So what we are seeing is that actually there's an area where there's a low cost required, and that's actually between 100 meters and 10 kilometers, since people are switching immediately over from like a very short range active optical cable to a telecommunication solution. And this solution is more than 10 times more expensive, and it's consuming quite some additional energy. So we think that especially if you're looking to silicon photonics or indium phosphide photonics, that this is a very nice area where they can actually come in. So here I made some comparison based on a paper of Krishnamurti to actually show like what is the current state of the art in power consumptions and where does it all fit together. So for sure it's about the cool bit, so we are consuming about 15 picojoule per bit. Then you have silicon photonics, where we are actually fighting to get the power consumption to be acceptable for a module. So the complete module from 100 gigabit is allowed to consume 3.5 watts, which is ending up in this 35 picojoule. And then for sure we also have the electronics guys that are still having a multi-channel electrical interface, and which is used at this moment for very high density, short distance communications. And the question is, who will be first actually meeting this target for about 1 picojoule per bit and be implemented in high performance computing? So our way of actually getting to that goal is by participating within the Foxtrot consortium, where we're using silicon photonics and making a fiber chip coupling there. We want to use 8 wavelengths, all running at a 40 gigabaud rate with a higher order modulation format, which is finally resulting in a 1.28 terabit active optical cable. So we are really scaling towards more bandwidth, we are scaling towards less energy consumption, and we want to comply to the longer length since it's single mode technology. For sure, our threats and challenges, of course, it's the 16 QAM, the higher order modulation, which is at this moment not feasible for datacom, so it really should be supported by the electronic chipsets as well. It's the power budget for the active optical cable and the power consumption of the active optical cable. Since for silicon photonics you still need an external DFB source, and if you're just using multiple wavelengths, the power is just scaling with the amount of wavelengths, whereas if you're going for higher order modulation formats, you're burning a little bit more of energy in the processing, but you're not scaling out with components and with additional power for these components. Another project where we are active in is the ADAPT project, where we're actually looking, can we use the area in between the bit streams, so like the idle patterns, can we switch off the driver and the driver control, the clock data recovery as well. So really focusing towards the electronics, since the optics is not consuming the energy, it's the electronics. So what kind of smart things can we do over there? With this, I would like to close my presentation. So if there are any questions, I'm happy to take them. Not with multi-mode fiber, but for sure VCSEL technology in the single mode field is evolving quite rapidly as well. So I can imagine that based on VCSEL technology, we would be able to make a single mode transceiver which can bridge this distance from 2 kilometers, but by using existing drivers, existing limiting amplifiers, existing assembly infrastructure, by just switching to different technology of the VCSEL.
Maybe I will try this one. So I was wondering, your 25 gigabit link was limited to 100 meters over OM4 fiber. Is that limited by dispersion, or is the market simply not big enough for you to make longer links?
It's limited by dispersion, but I think what I see myself, which is very interesting, is that the majority of the links is actually less than 10 kilometers. I think 10 meters. So 95% is less than 10 meters. So the longer lengths seem to be more or less like a niche market, but for sure the data centers, especially if you're looking to companies like Google, they're now not doing it only within one data center, but they just have like clusters of data centers that they would like to connect together. And these are relatively close to each other, but too far for active optical cables.
In the case of the transceivers for 10 gigabit Ethernet for MSA, multi-source agreement, the launching condition for multimode fiber is strictly defined using encircled flux. But for 20 gig or more, and for active optical cables, do you have the similar definition for launching conditions, or you can freely define the launching condition?
So that's the great news. What you see right now within active optical cables, people have more freedom to actually develop a lower cost transceiver. So if you're looking to like a standard transceiver, you have a transmit device and a receive device, and for sure they should be adjusted that you can communicate. So you have a standard that you need to comply to. For active optical cable, there's also a standard, but it's more like an electronic standard. So you have a certain amount of voltage that needs to come in and a certain amount of voltage that needs to come out. And everything you're doing in between is open. So in that respect, we don't need to comply with encircled flux. So we can use a reduced amount of modes to do our transmission over, for example, to extend the length of an active optical cable. So we can do much more tricks in that field, which is completely open.
Change in the agenda, and we're very happy to have here with us Dejan Gvozdic from University of Belgrade, who's going to talk to us about optical memories and flip-flops by stability and switching dynamics in injection-locked Fabry-Perot semiconductor lasers. So this is this one.
Okay, I would like first to thank Nikos for giving me the wild card to present the work of my research group. As he said, I come from the University of Belgrade, from Serbia, and there I wanted to give some facts about the university and the School of Electrical Engineering I come from, but since the time is limited, I will skip this part and briefly present my research group. At the time being, I am the head of the Department for Microelectronics and Technical Physics. The department deals with nanoelectronics, photonics, biomedical and ecological engineering. But at the same time, I'm also leader of the Photonics of Research Group. The group has 5 members. The first member is Professor Milan Mašanović. He is visiting professor of our faculty, and he is also with the University of California, Santa Barbara. He is some kind of external expert. Then we have one internal expert, Dr. Jasna Crnjanski, and she is actually expert for band structure calculation and of nanostructures. And we also have 2 PhD students working with us. So we have cooperation with Freedom Photonics with Professor Mašanović, and also we had cooperations with the Royal Institute of Technology and Institute for Telecommunications in Aveiro. Our current research is presented here, so mainly we deal with theoretical investigation and computation. So therefore, this kind of research is very interesting not only for the research itself, but it's also interesting for us as the users. So we are dealing with band structure and optical properties of multi-quantum well-active regions for various types of lasers, including Fabry-Perot and optical amplifiers. We also study, at the time being, stability and switching time in injection-locked laser diodes with respect to injection power and frequency detuning. And we also investigate static and modulation characteristics of reflective and traveling wave semiconductor optical amplifiers. In addition, our recent work is related to spectral properties of mid-infrared quantum wires and quantum dashes. So the title of my talk is Stability and Switching Dynamics of Injection-Locked Fabry-Perot Semiconductor Lasers with Possible Applications in Optical Memories and Flip-Flops. Actually, it is some kind of continuation of yesterday's talk of Professor Reiner and from France. And here the talk is more on the fundamental side, so I think it will be different than other talks. So in explaining this phenomenon, which is called bistability, we start from the slave laser, common slave laser, which can be, for example, Fabry-Perot laser. Here is the spectrum of Fabry-Perot laser. which is in the free running regime. And here is the dominant mode as 0, and all other side modes are also present in the spectrum of this laser. So the dominant light coming from the laser is the light of the wavelength corresponding to the wavelength of this dominant longitudinal mode. If we use additional laser, which is tunable laser, master laser, and inject the light into Fabry-Perot laser, then we can achieve injection locking, so we can lock slave laser to the master laser. Here it is important to mention that we should take into account very important parameter, and this is injected power from the master to the slave laser. And additionally, we have to take into account frequency of the master laser, which is usually different than frequency of side nodes. In that case, important parameter is frequency detuning. So the frequency detuning is actually the difference between the frequency of the master laser and the frequency of the side mode in which we inject the light into the slave laser. So these two parameters, injected power and frequency detuning, are two important parameters which should be included in consideration. Additional parameter can be side mode suppression ratio, which is actually the ratio between locked mode and the central or dominant mode of the slave laser. So in principle, we can expect that in the spectrum of the slave laser, we can have this dominant injection locked frequency and all other frequencies which are significantly suppressed due to injection locking. So injection locking itself has already proven successful in many aspects, and they are listed here. However, we are very interested in bistability phenomena, and I would like to show how the bistability occurs in this case. So we will focus now on the phase plot, showing the phase plot is something that is very common for dynamical systems, and it is actually time derivative of the quantity versus quantity. For example, speed versus position, or momentum versus position. So this is the common way to present dynamical systems. So the phase plot has nothing to do with the phase of the laser or something like that, but it's principle time derivative of the quantity versus quantity. In this case, this quantity is the carrier concentration or carrier density, and on this axis we have the carrier rate of rate of the carrier concentration, and here we carrier concentration. So here is the plot for free running laser, which means that the laser is slave laser in the free running mode, and we take into account the central and all other side modes which are present in the Fabry-Perot laser. So the phase plot looks like this, and in vicinity of the threshold concentration, we can observe the crossing of the phase plot and the n-axis. So this crossing is actually stationary point of the laser. This is the concentration of the stationary concentration of the laser in the free running regime. So the crossing itself is actually possible stationary point of the laser. This is the situation for the free running regime. So we do not have any kind of power injected into slave laser. But now, if we turn on the master laser and inject some power, then we can observe some bending of the phase plot, which occurs due to injection of light. And if we increase injected power, then we can see that instead of only one stationary point, we can have additional stationary point here. So further increase of the injection power leads to separation of this point into two. One is here, the second is here. And now for this injected power, minus 70.5 dBm, we have 3 stationary points. And in principle, we can expect that the laser can work in, or can find itself in one of them. So this is 1, 2nd, and 3rd. First, second, and third. So this second point, the middle point, is fully unstable. So the laser cannot remain in this point, so it can choose between these two, this one and that one. In principle, if we have 2 stationary points for a single injection power, it means that we are in the regime of bistability. Since we have 2 stable points, then we can switch between 2, can be in one of them. Further increase of injection power leads to the phenomenon where 2 points of red curve, these 2 are not important anymore, but this point and the last point will join and overlap each other here. So we have again 2 points, but here we have 2 points, one from this side and one from that side, and this one point is also stable. The other is unstable, these 2 which overlap each other. Here we have only 1 point. And therefore, we have the range of optical power from minus 20.5 till 15.5, for which we have 2 stationary stable states in the laser. Here I should mention that we work with the threshold, we work with the current which is 20% larger than the threshold current, and that we apply negative detuning, which means that the frequency difference between the master laser and a slave laser is negative. And we express this in units in omega, where omega corresponds to some quant of the frequency. So let me see, this quant of the frequency is 1.59 gigahertz. So 1 omega is 1.59 gigahertz. So it's approximately 10 gigahertz difference, this frequency detuning. Okay, now we can see that we have still 2 stationary points. And if I increase injection power even more, then this point that we had it here disappears, and the only remaining stationary point is this one, which corresponds to injection locked mode. So if we go back, we can simply recognize and see that this point is actually the point due to unlocked modes, while the point we have here is due to injection locking. Okay, now since we have 2 stable states, we can achieve bistability in the slave laser. And this results is actually obtained because we took into account all unlocked modes. If you do not take into account unlocked modes, then you cannot observe this effect theoretically. In practice, in experiments, you can observe the effect, but the reason cannot be explained. You cannot find the reason if you do not take into account all unlocked modes. If you do not take into account unlocked modes. So once we took into account unlocked modes, we were able to show that the laser will have 2 stable states. Here is the explanation for taking into account all unlocked modes. Here is the photon density versus carrier concentration for injection locked mode, m equal -5, for certain injection power and given the tuning. So you can see that the maximum of photon density occurs much before the threshold of the free running laser. So the maximum of the photon density can be achieved for smaller densities than the threshold carrier density. And this curve is actually phase plot when we have only one mode. And the common approach is to take into account only one mode, only injection locked mode. All other modes are usually neglected and people simply work with single injection locked mode. So this is the phase plot which shows only two crossings. This one, which corresponds to injection locked mode, and the second, which is, as we said, unstable. But if we add central or dominant unlocked mode, then we can observe that phase plot has one crossing, second crossing, and third crossing. So in principle, this reminds it looks like previous diagram where we took all unlocked modes. This point here, if we take only central unlocked mode, is actually unstable. So careful calculation or mathematics shows that this point is unstable. So we cannot observe two stable stationary points if we take into account only locked mode and central unlocked mode. We need something more. And if we take into account all other dominant unlocked modes, we can finally observe stability of the third point in vicinity of the carrier threshold. So this blue curve corresponds to the final results that you could see in previous slide when we take into account all dominant or all longitudinal modes present in the Fabry-Perot laser. So the most important thing is to take dominant modes, not only the central mode, but also all other longitudinal unlocked modes which have significant contribution. So what we want to do, we want to switch between two stable states. If we have two stable states, let's try to switch and try to change the state. So one way to do that is to apply change in the injected power. And you can see here what's going on when we change the injected power. So if we are in this state here corresponds to lower branch of hysteresis for side node suppression ratio. So here is the side node suppression ratio, and here you have injection power. So for this stationary state, we have this lower branch of the hysteresis. Once we increase the power that we have only one point, then the laser switches to the upper branch. And if we decrease the power, the remaining stationary point is this one, and the laser will switch to this point. So in principle, what we can do, we can switch the laser from two stable states to only one state, and this remaining state will become the state in which the laser will end up. So the way to switch is to simply increase and decrease power, and then we can observe the hysteresis loop for side mode suppression ratio. Or actually, if not, instead of side mode suppression ratio, we can equally well consider photon density of side injection locked mode. So this is one way to switch the lasers, to use injection power and to obtain hysteresis. However, we can also achieve the switching and bistability by changing the frequency detuning, and this is something very important. So by changing the frequency detuning, you can go through the states, you can go in to the case of single state and then enter the region where you can observe two stationary states. So in principle, the same thing that we can do with injection power, we can repeat with the frequency detuning. Interestingly, hysteresis can be obtained for positive and negative longitudinal modes, and the width of the hysteresis increases with negative detuning and decreases with increase of the mode orders. So you can see for different mode orders, M-1, N-5, -8, -10. So the width of the hysteresis becomes smaller and smaller when we increase the order of the longitudinal mode we use for the injection locking. Okay, so now we want something better. We do not want to make quasi-static switching. We would like to make dynamic switching. We would need some strong injection power to switch the laser from one state to the another state. This power must be strong enough, and in that case we can expect shorter time for switching. So we repeat the same thing, but with some injected power. So you can see this is the pulse. We switch the pulse from this one from the region from the middle of hysteresis, increase the power, and then switch the state of the laser. So you can see how it looks like. So this is the stationary state, and then you increase the power. Then this point moves toward stationary point, but if you switch the laser back to the right moment, you can end up in this stationary state corresponding to second bistable state of the laser. So the way to do that is to simply increase the power of the master laser and keep that power for a certain time. And this time, this duration of the master laser pulse is actually can be defined as a switching time. Of course, this time should provide switching for sure. And in addition, this is the switching time necessary for the slave laser to switch from one to the another state. However, switching of the slave laser is not over, and it can last a little bit longer than the time necessary for the switching. So we, in principle, can have two switching times, but I will talk about this later. So what you can see here, I will repeat once again, the switching. We start from here, and with this type of switching, we end up here. So this switching is switching from the lower to the upper branch. So increasing the power means switching from lower to the upper branch, so this is the switching up. However, so far I considered side mode suppression ratio versus injection power. But I have to mention, and this is very important, I think, that in addition to the photon density, we simultaneously change phase difference between the slave and the master laser. So this phase will change simultaneously with intensity, and we can provide actually phase variation during the switching between the states. In addition, you can see here that the phase has its own hysteresis loop, which depends on injection power. And this can be very useful thing, I think, because in this case, you can use on-off keying to achieve phase shift keying. Of course, there are some other, probably better ways, but it seems to be a very useful thing. Now you can switch the laser from upper to the lower branch by decreasing the power. Of course, this is delimited with respect that power cannot be negative, so therefore this limitation has to be taken into account. Therefore, this power must be sufficiently high that can provide a reduce of the power in this case. So this switching is switching down, and we switch from upper to the lower branch of the hysteresis. At the same time, phase switch from the lower to the upper branch. Okay, but since we have two kinds of switching, one is the switching of the master laser, the other is switching of the slave laser. Slave laser switching lasts much longer than the switching of the master laser. But we need to know what is the sufficient time to switch the master laser in order to finally achieve the result for the slave laser. So we have two different times. One is duration of the master laser pulse, which leads to the final slave laser switching. The second is duration of the switching of the slave laser after application of master pulse. Here I present master laser switching time in dependence on injected incremental injection power. Actually, this is the pulse intensity of the pulse. This is the intensity that we present on the view graph on the horizontal axis. So switching up is obviously much more efficient. It can take 10 picoseconds to switch the laser up, depending on the injected power. But switching down is such that it takes a little bit more time, almost 300 picoseconds in the best case. So in principle, we can achieve both things, but switching down is slower, while switching up is much faster. It should be mentioned that except 10 picoseconds, this switching consumes not so much energy. So the calculation shows that the energy consumption is about 2 femtojoules and can be even smaller. So depending, of course, on input parameters, laser structures, and so on and so on. So here I present switching times for switching down and switching up for different input parameters versus switching power. So you can see that depending on input parameters, we can cover a broad range of switching down times. However, switching up is very efficient and obviously can be of the order of tenths of nanoseconds. On the other side, on the right panel, you can see switching time versus the tuning variation. This is additional degree of freedom. And you can see that in this case, switching down is also very efficient. These results are derived from a relatively simple analytical model. So we derived an analytical formula which can be used to estimate these times. And we also did numerical calculation to check if this result is good enough. And in principle, analytical results are relatively good and comparable with numerical approach. And this is already published in a couple of years ago. Of course, we would like to make these times equal if it's possible. It would be fine to have equal times for this purpose. And we have some ideas how to make the times for the master laser switching equal. One is to shift the bias point or starting point on the hysteresis toward the left edge of the hysteresis. Second approach is to increase the photon lifetime in the free running regime for injection locked mode by introducing highly selective DBR mirror, which stop band is centered on the injection locked mode. So in this case, we might have a central mode like this, and the side mode, which is not suppressed, but almost equal as the central mode. So this is the second approach. And I'm going to present situation for approach number 1 alone, and then approach number 2 alone, and 2 combined together. So, starting with approach number 1, to shift the bias point here to the left edge of the hysteresis. This is the free running spectrum of the laser. So in this case, no success. I cannot achieve the switching in spite of the fact that bias point is very close to the edge of hysteresis. So if you decrease the power and increase the power, you cannot switch from here to there. Simply the laser goes back to his initial state. And here is the view graph showing the behavior of the switching of the slave laser. Then, if we look at the transient behavior of the switching up, we start from here, increase the power and decrease the power with this kind of pulse. I need pulse of 20 picoseconds to switch the slave laser from down to upper state, from down state to upper state. So you can see what is the common time for the slave laser about 100 picoseconds for the slave laser to switch up, and about 20 picoseconds for master pulse to provide the switching of the slave laser. So I'm not successful with this approach, although I want to be. However, if I decide to deal with the photon lifetime and to apply this modified free running spectrum and move the hysteresis bias point to the middle of the hysteresis and apply the switching, you can see the switching now. So if I decrease the power, increase the power, I end up with this transient regime. So with 100 picoseconds, I can achieve the switching, although I have a lot of relaxation oscillation and the slave laser oscillates toward the stationary regime. So now I'm more successful with the second approach. And if I check the time which I need for the switching up, it takes 25 picoseconds, and transition of the slave laser is very fast in comparison with this one, of course. And so in this case, we need 100 picoseconds of the master laser pulse. In this case, we need 25 picoseconds. So we have some improvement. At least we can achieve the switching. But now I combine approach number 1 and number 2. And then I end up with 35 picoseconds for the switching down and 30 picoseconds for the switching up. Now I have the bias point on the edge of hysteresis, and I use this modified Fabry-Perot laser. So now I'm much better. Now I have 35 picoseconds in both cases, and the relaxation oscillations are much shorter. Damping is better. But we have to understand the following thing, that this position, this lower state, is actually related to the free running regime. It originates from unlocked modes, and therefore we have these relaxation oscillations. If we want to get rid of these oscillations, we probably need to forget about this unlocked modes and try to deal only with the injection locked modes. So, okay, this is the situation where I used only injection power for the switching, but now I can decide to deal with frequency detuning. Instead of injection power, I will use frequency detuning as a switching approach. And I start with the pre-running regime again and the moved left positioned bias point on the hysteresis. So I have the switching for the switching down. I have 95 picoseconds for the master laser, and I need 55 picoseconds for the master laser for switching up. This is switching down, this is switching up. So 95 and in comparison 55. It's not so good, but it's not so bad. At least we have switching here. Then I apply approach number 2 with the modified free running regime, with the modified Fabry-Perot laser, but keep the bias point in the middle of the hysteresis. And then I have even worse situation, 130 picoseconds for the master laser and 45 picoseconds for the master laser for switching up. It's not so good, but if I combine two approaches, approach number 1 and 2, I achieve 50 picoseconds plus 55 picoseconds for the switching in the opposite direction. So now you can see that we can achieve much better results. Okay, now I have to hurry up and present a final idea we have at the moment. So we would like to get rid of these relaxation oscillations. The way to do that is to introduce dual injection, which is not new thing. So we can apply 2 injected powers and try to deal only with stationary points which are free from unlocked modes. And then we can probably improve the results. Here is the one proposal for all optical wavelength registry, which should which can be used as a memory for sequence of different signals with different color, lambda 0 and lambda 1. So this is one device that we proposed for application of this approach. Here is the mask layout. And at the end, I present some references related to this result we achieved so far. However, I do not want to give any kind of conclusion because the only thing I can tell you that we are confused, and it's very difficult to give the conclusion if you are confused with your results. The major thing that we need at the moment, experimental verification. At least we know we made some experimental studies. They are published in the paper number 2. So we verified that this hysteresis exists, but we do not know anything about the switching time and possibility to switch the laser with the frequency detuning. This is something that we have to further investigate. So instead of conclusion, I have confusion. Okay, thank you very much. So, at the time being, we are waiting for chip, which should be provided by JPIX. So we applied for this, and we're still waiting for this circuit. We hope that we can learn something from that, and at the time being, we do not have any other clue about the situation with the JPIX. Yeah, I do not remember figures, but in principle, so you can see on the mask layout that we made the circuit. It's difficult to recognize now, but we actually provided mask layout which is sufficient for making these 2 stages for these memory elements. So instead of Fabry-Perot lasers, we are going to use these micro ring lasers. It is the same thing, or more or less. So of course, instead of this, we can also use DBR, multimode DBR lasers. But in principle, all these components can be placed on the chip that was provided from the JPIX. And we hope that it will be produced soon. So I do not know exactly the numbers or figures for...
I asked something, what will be the gain material with this micro-ring laser?
This is 3.5 material, so everything is indium phosphide.
I would appreciate if we could go all outside here before having the lunch in order to have a photo of all the attendees of the summer school all together. So right at the front here, outside the door. So then we can have the lunch break. It's again at the semi-floor. And the students who have the posters can go after the lunch break and hang their posters. It's 1 floor lower than we are currently. So there is a region there with panels where you can hang up your posters. Okay, so enjoy the break.
We are now starting this session, and the first talk will be given by Kobi Hasharoni from the Israel company Compass EOS, and his talk will be about router optochips and interfaces.
Okay. So I'll talk about high bandwidth parallel optical interconnect, which we have designed and implemented into a router Optochip. But this is a general technology that could be used for any other technology application, actually. So first I'll talk about the motivation, the datacom and telecom bottlenecks, then our photonics solution, how we actually did the assembly and the packaging, and then, if you have time, the impact on network topology, because the whole idea here is to change the topology of networks and to improve them. So, which one is the laser? Which one lasers? Oh, so you can see slides like that in most conferences today. This one, for example, is from the Green Touch Consortium. It shows you the network, and it shows the hotspots, and you can see that the main hotspots are in the IP core and in the data centers. And at the same time, you'll be able to see these famous graphs from Cisco showing you the exponential increase in ICT bandwidth consumption. But most important is these graphs, which show you that the power consumption of ICT services, data centers, servers, core routers is increasing at a tremendous rate, I think like 10% per year. And this dotted line is actually showing you that about 2% of the, actually it's more today, more than 2% of the total world power production capability is being used to drive communication, which is huge. And the reason is that we're using huge systems, like the Cisco CRS, for example. These are huge, really huge. You need a forklift to put them. They're power hungry, and they require really complicated software, and they basically suck money from the service provider and eventually from the user. The reason, or one of the main reasons, is that most equipment manufacturers are using traditional electronics. And the two main issues are the speed and distance, the bandwidth distance product and cheap I/O. These two issues are limited, and the result is huge, complex machines. So before going into the solution, let's discuss first what are the problems. There are two main problems. The first one is chip-to-chip connectivity, or the bandwidth distance product. Here's a typical scenario. Traffic goes into DCMOS, has to go to that ASIC, which could be on another card or could be on another rack, actually. And of course, it has to go via copper lines. And as Richard explained very nicely in the morning, at high frequency, we've got the electric loss, skin effect, impedance mismatch, crosstalk, et cetera, et cetera. So the board designer basically has to put, every couple of inches, he has to put an equalizer, usually a DFE, which is an active equalizer, usually 2 or 3 taps, and that really translates into power. And on top of that, of course, the bandwidth distance is limited, because there's a limit to how much you can drive signal on copper. The next problem is actually much more severe, and it's usually overlooked unless you are a VLSI designer. This is cheap I/O. Because regardless of what you do in your CMOS design, what really determines the cheap I/O is the package itself, or the BGA connectivity. I mean, you've got to get data in and out of the chip. So the way to do it is either via the SerDes array or via the memory interface. They're basically the same, and they're all implemented using BGA. Now, a single SerDes, to those who don't know, is a serializer. Deserializer, it's the circuit element that transforms a parallel signal into a serial one and vice versa. So a single SerDes would consume 8 BGA balls. It's differential signal, transmit, receive, and you need 4 grounds. So each SerDes is around here. So you could say, okay, we can minimize the BGA ball diameter. I mean, you could get 100 microns today easily, and everything will be okay. The answer is no, because the main issue is not BGA technology, it's board design. At high frequencies, there's a limit to how close you can get the traces one to each other, and the breaking out from the chip to the PCB turns out to be a very complicated issue. This is from designing, so one of the FPGA user manuals, and it shows you how to do the breakout from the chip to the PCB, and it's becoming very, very complex. And the board designer has to use a lot of layers and buried vias, and it becomes a real issue, and the outcome is that in reality you can only use the BGAs on the chip, on the package perimeter. You can't really use BGAs in the center of the chip. So today the state of the art is about 150 SerDeCs at 25 gig, and perhaps in 2 or 3 years people will be able to go all the way to 200 SerDeCs per package, but this is more or less the end of the line, because you can't really make the boards more and more complex. You're coming to a dead end. So it's time for a new technology that will increase the bandwidth distant product, reduce power, reduce latency, increase the chip I/O, minimize solution size, etc., etc. Most importantly, it has to comply with NEBS. Those of you who don't know what NEBS is the reliability criterion for all telecom and datacom equipment. It's a bunch of reliability requirements. So it's not a science project. If you want really to make a device, a real device, it must comply with NEBS, and that's not easy. And of course, you have to revolutionize or significantly bring something new to the network architecture, because that's the whole idea. So the solution that we have designed is a parallel optical interconnect directly on the ASIC. So design your own ASIC. In our case, it's a core router traffic manager. It could be a switch fabric, a crossbar switch, a network processor, or an Ethernet switch, storage, whatever you'd like. And you put the optical interconnect in the ASIC. It's part of the ASIC with the 3 FIPS, of course, on top. So it's not next to the ASIC or close to the ASIC. It's part of the ASIC itself. And that implies, and of course, we want to use parallel optics because we want to maximize the bandwidth per square millimeter. And this solution must support a chip-to-chip, a board-to-board, and a rack-to-rack scenario using the same technology. So schematically, it would look like that. Here's your CMOS chip. Again, it could be anything. The analog electronics are directly in the CMOS, and you assemble the VCSEL and receiver matrices directly on the silicon. You package it, put it on PCB, and then you do the optical package using fibers, or in a few years, we will be using waveguides as well. The fibers go to the backplane, which is a passive backplane, so the entire connectivity between ASIC, which could be in this room and in the next building on the campus, is just fiber. The backplane is completely passive. So this technology is called IC Photonics. This is the artist version of how it looks. So what we really want to do is revolutionize the backplane connectivity. So traditionally, you would have your chassis. It could be a router, a blade server, whatever, with various line cards doing routing, storage, memory, whatever. And then you have the mid-plane, and then you would have the backplane. So this is kind of a cumbersome and really expensive design. Alternatively, you could have the same design, same line cards, same functionality, but there's no backplane, there's no midplane. The connectivity is photonic, and it's done in the backplane. And so naturally, you've got a complex system in this case, and a nice and cool system on the other situation. So before going into details, let's look at the evolution of optical interconnects. So we're all familiar with those edge-emitting pluggables, CFPs, QSFPs, SFPs plus. And in the last few years, Avago and Finisar have introduced the mid-board or board-mounted optical engines, which are one step further closer. They are in the mid-board. They are close to the ASIC, but to the CPU, but not really on it. And what we do, we put the optics directly on the ASIC, because we want to, as it's been mentioned a few times this morning, we want to optimize the system performance, and the way to optimize is to put all that stuff in with the silicon. So everybody's talking about silicon photonics all around the world. And it's a really nice technology. I've got nothing bad to say about it. The only problem with silicon photonics is bandwidth. We are talking about telecom and datacom, what's called big data applications. Silicon photonics today can deliver 100 gig, 400 gigs probably next year. And in 2 or 3 years, it might, with a lot of work, go to 1 terabit. With the parallel optical interconnect, we can do 1.3 terabit full duplex today, and we are on our way to 10 terabit in a single chip in 2 years. So it's a great technology, silicon photonics, but it's really not useful for big data applications like a core router or a big switch blade server. So let me walk you through the design and packaging aspects of this optical interconnect. So the first element that you need is the VCSEL. Now, we are using two-dimensional matrices for the VCSELs, for the fibers, and for the diodes. And since we are putting the transceiver directly on the ASIC, we have to flip chip it directly on the silicon. Now, a typical VCSEL at 850 would emit light from the top surface. Here are the bumps. But then you are flip chipping it onto the silicon, so you'll be shooting into the silicon. So you can open holes like IBM did, but since you have down here, you have a real ASIC, a logic chip, you can't do it. So what we did, we flipped the illumination, so it's a back illuminating signal. The light goes through the gallium arsenide or indium phosphide substrate, and because gallium arsenide absorbs at 850, we redshifted it to about 1,000 nanometer. So you can see the eye diagram, it's really nice and open with very small jitter in it. Why would you like to use VCSELs? I think this image shows you the reason. These are real wafer probe data from the gallium arsenide VCSELs, wafers, and you can see that there are a few important things to see here. First of all, the homogeneity of the optical power, the threshold currents, the resistance is great. These are really nice devices. And most importantly, and you can do, of course, wafer level probing on the wafer level, so that reduces cost. And you can dice the VCSEL to practically any dimension you want. It depends on the yield. So you can actually implement a matrix. If you would be using side emitting, DFB, indium phosphide lasers, you can't really do a matrix. So this is probably the biggest VCSEL matrix in the world. It's 12 by 14 VCSEL, 168 channels. You can see the eye diagrams. This is a PRBS 31 pattern. And again, the size, the 12 by 14, is a function of the current architecture that we have. You can actually dice it to any dimension you want. Similarly, with photodiode, this is a 12 by 14 matrix of photodiode. We measure the responsivity of the photodiode throughout the matrix. One of the biggest issues with VCSELs is thermal management, because this is a telecom device, and if the VCSEL power fluctuates significantly, you are going to end up with bit errors. On top of that, we put the VCSELs in probably the most irrational place. We put it directly on top of a 80-watt silicon chip, CMOS chip. So you could say, you're fucking nuts. So the idea is, how do you maintain the temperature? How do you stabilize the VCSEL operation? So looking at the VCSEL top layer, the miser would be down here, so anode and cathode. So we put two thermal dummy electrically isolated pillars, and you hook them to the biggest metal planes in the CMOS. So of course, some of the heat goes by radiation, but the vast majority of the heat goes via those thermal pillars to the silicon. Now these metal planes are actually a heat spreader, so heat is being pumped down. And then, of course, there's a heat sink with forced air cooling. Does it work? Yes. Here is a measurement of about 3 months. This is the actual optical signal on the photodiode from the VCSELs. This is from about 10 or 15 different VCSELs on different ASICs, on different boxes actually, all coming to the same photodetector, different channels. And you can see that the optical signal is fairly stable. So this shows you that this thermal management scheme works. And this is what you really want. You want a stable VCSEL signal. So now you have to go to the ASIC design. And again, the logic design could be anything you wish. We are a telecom core router company, so we did the digital part. We have queuing, egress processing, egress buffer, switch fabric. It might sound like gibberish to you, but these are elements of a core router design. And they are all around. In the center, you can see the analog macro. So you have a transmit macro and a receive macro. So each one is 250 by 2, there are 168 pixels down here. So in the transmit macro, you would have the laser driver and the serializer. And in the receive macro, you would have the TIA, the LIA, the equalizer, the clock data recovery, and the deserializer. Now, so this is a mixed signal chip, actually. So we do everything in a regular TSMC, in this case, 65 nanometer process. The current chip is 16 FinFET process. and you have you have the logic part here, and about 10% of the total silicon area is actually used for the optical interconnect itself. So this is what, when I say that we brought the optics to the silicon, it's this. The optical transceiver is actually an integral part of the ASIC, of the DSP or CPU, whatever you do. The analog macro, or the transceiver itself, schematically looks like that. So you have low-frequency digital lines. Why low-frequency? Because you can't really go, with CMOS, you can't really go more than 600 or 700 megabits. It depends really on the CMOS technology. At 60 nanometer FinFET, you probably can go to 1 gig. But these are low-frequency lines anyhow. So then you have a serializer, which takes the parallel signals into a single analog lines, laser driver, and the VCSELs. And notice that the distance between the laser driver and the VCSEL itself is about 100 microns. This is important because the last thing you want is to have a transmission line. If you have a transmission line, you're probably going to do you're going to get some parasitic capacitance and inductance. You're going to waste a lot of power on cleaning it. So maintaining a very, very short distance between the VCSEL and the laser driver is crucial to this design. Then you have the fiber link, which could be 200 meters. It depends on the dispersion. So 200 meters or 100 meters in about a year and a half. And then the reverse path, the photodiode, the TIA, the LIA, the equalizer, the deserializer, the clock data recovery, and then you have the digital lines once again. So now you have your 3.5 lasers and detectors. You have your silicon, you have to put them together. But as we all know, there's a big CTE difference between 3.5s and silicon. Here's a finite element simulation showing a piece of silicon with gallium arsenide on top, and we apply about 200 degrees of thermal gradient, which is common to assembly. And of course, you can see that the CTE differences are big, and basically if you do it straightforward, it will break. What we do in reality, we grow high aspect ratio gold pillars between the silicon and 3.5. Why gold? Because it's the most flexible and malleable material. So upon when there's a mechanical stress in assembly, the gold will deform, but will maintain the connectivity. This is how it looks in reality. This is on a silicon dummy wafer. So you see the anode, the cathode, and 2 thermal bumps. If I blow it up, this is a gold bump before assembly. It's been reflowed. Actually, we have a little bit of tin on top. So we're using eutectic gold tin chemistry. We flip chip assemble it, and after reflow, this ugly stuff down here is actually very beautiful. This is the eutectic intermetallic phase, which is a combination of gold, tin, and copper. Where did the copper come from? You can't really put gold on CMOS. So we plate copper on the CMOS, gold on the 3.5 with tin, and we do the flip chip and reflow. Then we go to the actual assembly, again using flip chip. So you can see actually the laser on top of the silicon. You can see the gold pillars. And here again, some different angles. So now you can see the laser and photodiode matrices flip chip assembled directly on the silicon. Here it is. Oops, sorry. Here it is once more. Here's the ASIC. It's a relatively large ASIC. It's 21 by 21 millimeters. We have about 7,000 I/O bumps for memories, clocks, grounds, power around. I think this is one of the highest numbers. Actually, we have the next version. We have already 11,000 bumps. It was assembled about 2 weeks ago for the first time with 11,000 bumps. VCSEL matrices flip chip assembled onto it. Now, there's no way you can put 7,000 bumps on a PCB. The pitch is too small. So you have an intermediate board, what we call a substrate, which is also actually a small PCB. But notice that we have a cutout hole in the center because we need to optically couple the photodiode and VCSEL matrices. So here's the back surface. Here's the silicon itself on an organic package. Now you can take this chip. Of course, there's a regular BGA matrix here. You can take the chip and send it to any PCB assembly house for regular assembly. So far, we have done the chip assembly, chip packaging. So now you'd like to do the optical packaging. You need to connect the fibers to the VCSELs and photodiode matrices in order to move them to the backplane. So in order to do that, you have to use your 12 by 14 fiber bundle. Again, each VCSEL, each photodiode, they have their own unique fiber. So you need the fiber layout to be identical to the VCSEL and photodiode layout. So we package the fiber ribbons actually in a matrix format. This is how the fiber bundle looks like. This goes above the VCSELs and photodiodes, and on the other side you have regular floating connectors, because this is a line card, so you need to be able to insert and remove it in a floating manner. In order to do the coupling itself, you need some micro lenses. So we use a simple scheme. It's called a two-lens relay, where the light beam is collimated between two lenses. So one lens is assembled on the lasers and detectors. Of course, we use gallium phosphide again because of the index similarity. These are high index materials, and the CTE differences, it has to match. So it's a high index lens here, and on the fiber edge, this is a gallium phosphide matrix, and on the fiber, we have a regular Pyrex lens. And again, everything is 12 by 14 again, because each channel has its own optics. Now, why is it important to have collimated optics between the two lenses? Because that simplifies your assembly tolerances. You're using multi-mode 50 micron optics, so, and you have quite a large number of, you have 168 channels. Alignment is not a trivial issue here. So with this collimated beam approach, your alignment tolerance is actually very much relaxed. Finally, it looks like that. So here's your transmit, and here's your receive fiber bundle. It is assembled above the chip. The chip is actually on the print side of the board, the other side. And we have some metal blocks that actually hold it. And it's being glued. And this is actually a full router. A little bit of performance. So we can look at the sensitivity of this device. So 10 to the minus 12 bit error rate. We consider the power budget is about minus 8 to minus 10 dBm. Since we have about 2 to 3 dBm laser output, we have a dynamic range of about 10 dB, which is huge. So this allows you for alignment errors and for aging and any other effect. In reality, we don't really use this budget. Looking at the receiver side, this is the receiver jitter tolerance. You can't really see the numbers, but this is a really nice number. It's actually better than the 10 gig Sonnet standard. The most impressive result is this. This is a CDR test pattern, because one of the key design features of this is the clock data recovery. The receiver side must be able to extract the clock from the data. You don't have trigger. So you send 63 ones, 63 zeros, and 2 1010 bits, 2 single transitions. This is the most difficult pattern for CDR to follow because of DC offset issues, and you can see that the CDR was able to follow the signal completely. So this is a really nice design. So some numbers to show off. So we have the highest reported aggregate bandwidth, 1.3 terabit full duplex, 1.3 going in, 1.3 terabit going out, and the data density is 64 gig per square millimeter. So this number actually explains why we have such a high bandwidth, because we are a very packed and efficient, this is a very efficient assembly. The power efficiency at 65 nanometer is 10 picojoule per bit, which is rather good because it includes everything, including the SerDCs, the laser drivers. And again, like it was mentioned earlier this morning, correctly, most of the power dissipation is not from the optics, it's from the electronics itself. The VCSEL link itself is not really such a high power dissipating element. Most of the power comes from the laser driver and from the serializer and deserializer. So the evolution of this technology, so we are doing it today with fibers, and under the environment of Foxtrot, we are moving into waveguide technology because it has the potential of simplifying the assembly, because chip-to-chip connectivity does not really have to be done using fibers. Fibers are more adequate for rack-to-rack connectivity. So chip-to-chip and actually also board-to-board connectivity could be done via waveguides, waveguides on the backplane. So we are very active in this region. We are able to do two-dimensional scans, and we are usually with our partners in TTM. We are doing mostly scans of buried mirrors in the waveguide structure. And hopefully in a few months we will be able to show a PCB with two of these chips, kind of difficult to see. So there would be a single PCB with two chips communicating via optical waveguides, hopefully. So now let me go finally talk about the impact on network topology. Because again, this is the reason why this project actually started off. So let's look at the typical scenario in network design. So you have some kind of a fabric element, or a node as they are usually called. This could be a memory controller, a storage controller, or some kind of an internet switch. It's a node. And it's connected to a crossbar switch because you want to be able to move data between those chips. So the node capacity, so if you want to increase your node capacity, you can, of course, you have to add more crossbar chips. But at some stage, you're going to come to a dead end because there's a limit to how many SerDeSes or chip I/O. There's a limit to the chip I/O that you have. So the amount, the network size is actually limited because you have to add more and more crossbar switches, and eventually you will not have enough chip I/O here to connect to the crossbar switches. On the other hand, looking at the crossbar itself, if you want to increase the number of nodes that the crossbar is connected to, so naturally the crossbar is limited again by the number of SerDeSes that he has, because if you want to add more nodes, you are limited again by chip I/O. So either way you look at it, you are limited. Your system scale is limited, really limited. And I guess most of us are familiar with class networks. So here's combining the two problems together. Here's a simple example. It's very simplified. So we have 4 nodes and 1 crossbar chip, and I want to add a 5th node. But I'm out of SerDeSes here. So actually what I have to do is increase my crossbar 6-fold. So from 1 crossbar, I went to 6. So this is called a 3-stage class network. Because if I want to have a complete connectivity between all 5 nodes, I must have this really complicated class network. So in reality, what it means is, of course, the complexity and cost go up, but more importantly, or I don't know what's important, the power latency increases as well. And this is the big issue. And of course, if you're using an active optical cable to connect those elements, you have to add more power for that. So what we really wanted to do is to break the chip I/O limit and allow simplified network architectures. So going again to the traditional electrical chip, which is only a BGA matrix. So let's assume in a few years that people will be able to do like 180 SerDeSes on a package. It's difficult but doable. So they would have about 5 terabit on a single chip. With the optical technology, you will have again the same 5 terabit from the electrical SerDeSes. On top of that, you have, for example, with a 336 element matrix, which is what we do today, you will have an additional 10.7 terabit. So it's a 3-fold increase in the chip I/O capacity. And this 3-fold increase has a huge implication on network design. If I plot it graphically, so here's let's do some kind of a closed network, and I'm plotting the number of chips or switches required versus the network capacity. So with the regular technology, you can see the slope, and this kink here is a transition from 3-stage switching to 5-stage switching, already at 120 terabit. With the optical technology, because you have 3 times the chip I/O, you can see the slope, and it's a single-stage switching. In fact, you can go all the way to 1.6 petabit, which is a huge number, in a single-stage switching capacity network. And because service providers are worried mostly about money, it is very appealing to them because they don't have to use chips. The number of chips is about 10 in this technology versus this in very, very large-scale networks is about 10%. So this technology allows to reduce the number of chips required, and of course you can realize the biggest full mesh network you want, because a full mesh network where you have a direct connectivity between ASIC is a direct function of the chip I/O, so you can have the biggest mesh network in the world or other switching networks. Here's some kind of an example. This is a typical blade server data or blade or server blade scenario. So you have 15 blade servers, memory, storage, CPU, whatever. And it's a cache coherent system, let's assume. Cache coherency means that the CPU down here has to access a memory or another CPU on this line card. With traditional technology, very, very quick, at least in this system scale, you would have to put a couple of switches in the center because you can't really handle the chip I/O. Putting more chips in the center means that your latency is very long and the power consumption is high, and not to mention that the complexity of the system is huge. Anybody who's been into a real hub, like, I don't know, in Europe, the Deutsche Telekom hub, for example, or France Telecom, these are monstrous hubs with thousands and tens of thousands of fibers going in and out of the switches and routers. If this was a cache coherent system, usually cache coherency requires that the CPU here accesses and retrieves the data from a memory, for example, here in 150 nanoseconds. But this kind of a centralized switch will consume, the latency will be 120 nanoseconds. So you actually don't have any time for the flops to do the actual work that you really wanted, to access some memory. So this means that the latency is long. It's too long. So alternatively, with the optical technology, what you do direct fiber connection between the ASIC. So the CPU down here connects directly to the CPU or to a memory controller down here, and latency then becomes the latency of the optical channel, which is a few nanoseconds actually. So this is the power of these systems. So going to what we have done in Compass, so we have implemented a full mesh networks. Now with full mesh, let's suppose I have 4 nodes and 4 switches. If I increase the number of nodes, the node bandwidth, or the number of IOs, or the number of nodes, I can go to multiple planes, what we call, and I can increase my mesh network to very, very large size. So this was actually implemented in real life. So this is a real router. This is the Compass router, where we have 8 nodes or 8 ASICs communicating in a full mesh scenario. So there's 160 gig going between each ASIC, and the size of this router is 6 rack units, which meaning something like that. A similar Cisco or Juniper router is probably bigger than I am, and it's all due to the optical connectivity. If you want to go to multi-rack deployment, so you can take this single chassis, you can add another chassis, and all you have to do is plug a fiber between them. No switch is required. And if you want another one, you put another, and you plug another fiber, or a cable. It's a bunch of fibers. It's a cable. And another, and another. Actually, you can go all the way to 1.6 petabit. And again, this is a huge network architecture. So 1.6 petabits, which in a switchless solution, meaning that all the boxes are connected just by fiber jumpers. So this kind of network topology is actually impossible to do using regular chips like from Broadcom, for example, because at around 50 or 40 terabit, you would probably come to a dead end in terms of connectivity, and you would have to start putting more and more switches, centralized switches. So this direct link gives you full connectivity, and for us from the routing community, it gives you a high speed up. When you have high speed up, you can actually do many routing related tasks. So to summarize, cheap I/O and bandwidth distance product are the dominating factors which limit the IP core and the DC data center networks. So this high bandwidth optical interconnect solution really enables to open up this bottleneck and allows you to implement really very, very large network topologies. So with this, I'll thank you.
About your big scenarios that you showed before, can you
in theory, yes. There are two things. You said bad coupling to the fiber and package them close. These are two things. Yeah, you mean multiple fibers.
Yes, yes.
Yeah, you could in theory, but the issue is that it's the analog. I don't have this. It's difficult to see here, but it's impossible to see. But this is actually made from 168 small cells. Each cell is connected to a laser. It's 250 by 250 micron. So even if you go to 60 nanometer FinFET technology, which is the most advanced, even then this 250 by 250 cell is completely packed with the electronics. TIA, LIA, equalizer. Today we're thinking about PAM4, so PAM4 also requires space. So even if you really, really want it, you can't really, 250 by 250 is really on the limit. So you cannot really go to a smaller packaging because you will not have enough space for the electronics. On a very, very small system scale, of course, you can do it. Of course, you can wire bond somehow the analog electronics to the laser from the side. But when you have a large scale matrix, today we have 336 elements, it's impossible.
Sort of a related question. Where do you put the heat spreader or heat sink?
The heat sink is below the silicon, physically, but the heat spreader itself is actually one of the CMOS metal layers.
So your bumps, your silicon is flip chip, but like through the top, right? Where the So that way you put the heat spreader sort of underneath.
Yes.
But it's just so the heat spreader is still sitting on the PC board, or
No. So, and maybe heat spreader is not the right word, but the thermal bumps, and actually also the anode and cathode, if you think about it, are physically connected to metal planes in the CMOS. Voltage supply usually.
Sure.
So these are the heat spreaders. So these are the biggest, thickest metal planes. So they spread the heat.
So that's from the VCSEL to the ASIC. Where's
Yes.
the heat spreader?
Oh, it's down here. So the heat sink is assembled down here, and we have forced air cooling going through the fins. So heat is actually being pumped down.
Okay, so where's the PC board?
Oh, the PC board in this diagram will be up here. Kind of. Where is it? So once again, this is the CMOS, this is the laser. So the heat sink would be down here. The PCB itself is up here. So it's an inverted assembly. Okay.
Just in terms of scalability, you show maybe you have like 5x more before you cover the whole surface of the electronics with VCSEL arrays, right? Maybe from 1.8 to 10 terabits per second. How do you see growth beyond that?
Beyond 10.7 terabits? It's all a question of how much logic do you really use. Okay, the design of the analog, the power supplies to the analog macro are actually coming from the side, from both sides. Okay, so each row is 12 elements. The 12 comes from the fiber industry. I have no idea why, but it's standard. So the power supplies come from both sides. So each 6 elements get the power supply. So in theory, you can increase this matrix as long as you maintain these 12 elements. Actually, you don't have to maintain anything, but you can increase the matrix size as much as you want in this north-south direction. It's a balance between how much logic, how much space you need for logic. So it really depends on the system architecture. This is a very heavy DSP. The logical tasks that we do are it's a very complicated ASIC. So it's kind of a compromise. The 10% are for the I/O and 90% are for logic. You can flip it, play around with the numbers.
Any other questions? Yes. In the actual router system, all type of channels are operated fully operated, or some channels are used for backup or redundancy?
Yeah, some keep some of them operating, but not with traffic, just with dummies. And some of the VCSEL actually switched off. So far, we have not encountered. These systems are actually in real production for more than 2 years. So I think most of all the traffic from Japan to California is going through those routers. So they're running into real traffic. Also, one of the biggest video cable TV provider in the US is running this. So these are real systems in production, and we've not noticed any reliability. Of course, we've done lots of reliability issues, but we have built in redundancy anyhow.
Is your cooling structure an active one? No.
Just posted.
Sorry?
The cooling?
Yep. And could you go back to the slide where you show the VCSEL wafer homogeneity? So while the slope efficiency and the series resistance measurements looks quite homogeneous, the optical power looks like if there's more power coming out of the central part of the wafer. Is that true, and why is that?
It's really related. First of all, the high power region is actually part of the measurement chuck. So this is, I think, also a measurement issue. The variations are small. You're correct. In principle, you're correct. There is a little bit of high power in the center, but it's from here to here, you have several tens of thousands of lasers. So when looking at a real matrix is, I can't really show it, it's really small, 12 to 14. There are about 800,000 or more lasers on a wafer, 3-inch. So on a matrix scale, it is very homogeneous. In the wafer level, you're absolutely right. Part of it, by the way, is the measurement chart. It's something we know. But there is some homogeneity, absolutely.
Yes. You mentioned earlier in the talk that silicon photonics is much smaller bandwidth density from the chip than VCSELs. Can you comment on that? Where is that number coming from? 0.1 terabits per second per chip.
Most people are doing today are driving 100 gig interconnect with silicon photonics.
That's for one vertical top.
I agree. But if you look now, if you look at the data at the density per square millimeter, it does not compare.
Well, what I'm saying is, through that one vertical coupler, you get 100 gigs. And you can put a lot of those.
Yeah, but this single coupler is about 4 by 6 millimeters, give or take, plus minus. If you look at the entire silicon photonics assembly, and we look, it's not a very, very small design. Maybe the things that Fabrice has shown yesterday are a nice way to go. But the current technology with the splitters, MZIs,
not like that. If you look at Oracle demonstrations, like from last year, like for PPL, actually PPL 2012 papers, it's 100 gig per one vertical coupler, the ring resonators.
But what was the footprint of this single vertical coupler?
The coupler is 20 by 20 microns.
That is the big coupler.
But you do have ring resonators, etc. So if you look at the overall real estate of optics, it's maybe 100 by 100 micron, but it's still 100 gig coming out of tens of millimeters squared.
Not only with the auto work, but eventually we need more than 1 terabit I/O. If silicon photonics can provide it, I'll be the first one to use it because we have a real issue with long distance, as you probably can figure out. 2 kilometer interconnect. Once silicon photonics is there, we'll probably use it. But today, I don't think there's anything. I don't think that silicon photonics, with all due respect, will be able to go to 10 terabits on a CMOS. And that's where we are going. But again, I have nothing bad to say about it. It's not. I think there are many arguments. I think you were at the MIT symposium in March also. So there are many the debate between VCSEL technology and silicon photonics. I think these are parallel. They are matching. There will be able to live side by side. So VCSEL technology is probably better for very high bandwidth. Silicon photonics has its own merit. What happens in 2020, 2025, let's see.
I have one last question. You said that the power budget of the link will have 10 dB excess loss, plus 10 dB margin. Do you ever consider using pump 4, pump 8?
Yes. Considering in this generation, no, but we don't have enough space in this 250 to 250 to put the PAM4. But one of the reasons to go to 60 nanometer was to put PAM4. Yes, absolutely. PAM8, I don't think so. The signal generation is not enough.
Any questions? Okay, so let's the speaker again. Yes, hello. And now the next speaker is Immonen from TTM that will give us present us work about Optical PCBs, the new motherboard.
Thank you. Yeah. Okay, this is a bit high. Okay. Good afternoon. My name is Immonen. I come from TTM Technologies. TTM, let's not look at our presentation. Let's go for the first slide. I was planning to be quick, but not that quick. Okay, going to directly to the last. So I'm going to continue talking about, let's say, a bit more of the building blocks for these, let's say, next generation technologies that we've been, let's say, highlighting and hearing very good overview presentation and requirement introductions in the morning. So this talk is going to be, let's say, titled as the Optical PCB, a new motherboard. That's something I try to elaborate. First, we go quickly through the motivation. I think we have been motivated well. We look at the, let's say, optical interconnects for system links, quickly going through the optical printed circuit board technology, what we have been developing at the TTM. That involves now the polymer waveguide technology, and I will talk of something about the coupling light in and out from the waveguides as well. And then I show some product examples and try to close my talk. So first of all, let's say start defining what we're talking about generally. Printed circuit board, that's what you have in all your systems. So essentially, it's today, it's really a custom designed unique and market product forming an interconnect substrate that fundamentally comprises of a dielectric players, fiberglass closures, various other items, and obviously a conductive pathways, the copper traces that provide your functions for connections between the layers and as well for the components. So this is the, let's say, the building block that is sitting in each of the systems. The copper trace features, there was highlighted earlier in the morning presentation that these printed circuit boards itself, they are very, let's say, complex today. What we see, and let's say in our terms, the critical technology parameters would be the line width and space, number of layers, hole size, aspect ratio, material type. And these really come in various flavors and a lot of varieties. I show here in a very small picture, there was a lot of talk on the complexity or the packaging and integration. And as well, PCBs obviously has been developed over the past years, over the 10 years, 20 years, to a very high complex structures. So obviously these comes in various flavors and various forms. We have to cater, this is let's say a glimpse of a TTM technology PCBs that we fabricate, and as well, we of course have to make a product for each purpose or end market. We can see obviously rigid PCBs which comes up to 60 layers of metal layers in there. We have their embedded passives, heavy copper layers for thermal management, and with various thicknesses, sizes, and dielectrics. Then another form of PCBs might be the high density. These you have in your mobile sets, tablets, and these kind of a product. It's a very complex. Actually, the factories say that the typical infrastructural boards are, let's say, more conventional, and the build-up boards are very difficult to fabricate. Then we have a combinations, rigid and flex boards. We have RF microwave specialized boards. We have IC packages as well in our company. that they provide packaging substrates, very fine features coming from multiple layers, different buildups, different exotic materials, and a wire bonding or different kind of bonding features, cavities, elements. And of course the specialty products for military aerospace products as well. And there you can see the layer count can be very high. There we have a special dielectric materials. There was talk about the obviously the electrical signal performance where you really need the different materials. No, I'm really not accommodating with this one. So very quickly motivating. Obviously the morning talks, they have been giving us a perspective. The data rates are increasing. The standard, I'm showing this only, the standard graph showing that 40 and 100 gigabit Ethernet, this is an Ethernet standard perspective, has been ratified already. 400 gig is evolving. This means the bandwidth is increasing. And obviously we see that to cater the applications that Kobe was just highlighting, we are not able to do that with the, let's say, parallel SerDes lines. Simply the layer counts, as Richard pointed out, the layer counts are increasing. The traces have to be closer to each other. We need to go for higher data rates. And what that means to us is many problems. So PCB will obviously will start to suffer. The various items that was already highlighted in Richard's presentation very nicely. High loss crosstalk reflections in various locations of a system. We see those in a vias, in a traces, in a connections, and that will impact. And there's a, let's say, very minor short glimpse of eye diagrams, and that's been measured now in 12.5 gigabit and 25, and for certain materials or certain glass types or various other factors, the eye is closing. So obviously the techniques that were touched and said are going to be required to tackle with this issue. So we can, from our perspective, what we see and what we've been forced to do and realize is that the PCB laminate will be as well a foundation to high speed. We see now that the current, let's say 12 plus gigabit technologies in the next generation 25, in that case we are much more prevalent to driving the use of high-speed materials, high-performance foils, denser components and techniques. And we obviously, on our side, it means many items, as well as new very low-loss, very capable materials. And that's changing a new material set or taking a different process for that one means various items. You have to provide, at the same time as you change your set of materials and design sets, you have to able to provide the process, cost effectiveness, provide that reliably, and be available to do that, not to compromise the electrical performance. And having said that, it's difficult, it's doable. So we really see that the 25 gigabit signaling is coming, and this is an example of interoperability demonstrators shown at ECOC last year. 100 gigabits is this time the 4-channel 25 gig over 27-inch link, so card to backplane to card implementation. So this just highlights that, let's say, without any real practical solutions, we are stayed on copper side as long as we can. And as well as was pointed out in the roadmap discussion in the earlier talks, we've been, let's say, looking at the trading space. When would the optical be, let's say, competitive to copper? Again, the copper survived now 25 gig, and we need to see that the 56 gigabit channel transmission activities are ongoing. So copper has always, let's say, kind of failed or succeeded passing the roadmaps as we were projecting them to do, and it's been happening to 25 gig signaling as well. But the 25, providing a 25 gigabit data rate on a PCB having a multiple layers is going to be very complex. And this is now kind of a process view for that matter. Fabrication challenges are enormous. We have to provide multiple layers. We have to provide, as was pointed out, we need to put the traces closer. We need to add the layers. We need to go for mechanical, electrical properties, and the tolerances much more narrow. So that means the inner layer spacing requirements are increasing. The drills are getting smaller, and the boards are getting thicker. That means the aspect ratio is getting higher, and it's going to be very tough. The form factors, the board sizes are enlarging because you have to accommodate all those signal layers and traces, and materials for the applications will move. And the signal data rate is increasing at the same time. And the impedance control and tolerance over that large and multiple layers, the requirement is getting tougher. So at the same time, all these, let's say, impacts, they are not going to, let's say, come at no cost. So this is, let's say, a projection of, let's say, system vendors' point of view, the cost side of the story. Currently, let's say, in a certain, let's say, switching routing, blade server, low end to high end, cut up, the PCB represents roughly 30% of the bill of materials. And that these particular technologies that I just, let's say, highlighted in an earlier slide are going to contribute that number significantly. So not only, let's say, the material itself, but these novel technologies that did not exist too much on the, let's say, high layer count factories earlier, which were, as I, let's say, started describing that, like in TTM, we have multiple HDI and rigid flex technologies. These are going to be needed. These boards require several additional new technologies to be added besides the tough requirements on the mechanical side. And if we look at the material side itself, we see that even a certain very high-end materials like MEC6, which is a very low loss and having a confidence across the next generation 25 gig material, the cost can be in certain, let's say, product segments significant. So it's a significant contributor, and it will. It's been pointed out that it's as well very much design dependent. So depending upon your design, your impact for certain material base is different. So the industry has been, let's say, interested to look at the alternatives. And the optics obviously is a one. So as well, TTM has been motivated to look at this question for several years, and more recently, let's say, more effectively. And these were the, let's say, copper to optical comparison or metrics, and obviously merits on the optical side. And these were very nicely covered. So low loss traces, no EMI, higher capacity, where we are able to provide longer traces, higher channel data rate or density, particularly, with several other advantages. So obviously what we're seeing, and provided already the roadmap pictures, the fiber is getting closer to the processor. And this is the, let's say, technologies and products that we see in the market. So they are mainly based on the fiber. So this is the Avagos technology for that one. So putting optics actually to this spot, going to the edge, and then provided that coming to the fiber. So the existing solutions in the market, yes, can provide a very much a bandwidth, and Kobe's presentation previously provided a further improvement for that one. But what we are interested in, let's say, to look at the next generation beyond that. We are really developing and looking at alternatives to embed those optical traces, embed or have them on board or directly connected, but essentially being part of the system itself, the boards. This is just the cross-section of a potential card backplane in implementation, but obviously the implementation can be a mid-plane or just from the card to the edge, a shorter link type of solution or chip-to-chip interconnect. But fundamentally, what you need in this construction is that you obviously need to have the optical channel buried or placed on your printed circuit board. But to have that functional, we obviously need the optical engines or transmitter devices with interface and waveguide. So with the fiber-terminated solutions, yes, we can do something, but in the end of the day, we need the packaging solutions that can provide you really the light into the board. We need various optical connectors or connections, interconnect points. First one would be the light coupling from chip to the board with the waveguide. The second point would be having a connector from card to another card, and various others, kind of mid-plane solutions. Wherever we want to have the signal get it out and coupled in or out, we need a connection point. So this is really the, let's say, the the graph, and which as well highlights that this is not only a, let's say, PCB suppliers, a transmitter device developers problem. We need to work together. All the ecosystem has to be in place in order to really put this into work. And the channel itself, I'm putting it to a couple of graphs to point out it can be a step index multimodal, gradient index multimodal, or even a single mode at some stage as we now develop in the Foxtrot project. So the application space obviously is those systems requiring kind of defining the key metrics, power consumption, interconnect density, bandwidth, length, and the cost features, large HPC systems, cloud computing, high capacity routing and switching, and network data storage that we're all covered in the morning. So going then, let's say, a step further, the PCB that we're talking about and developing is, let's say, looking like this one. We do have a hybrid construction. We do have couple layers providing us the power distribution and utilized for low signal speed. So fundamentally, you would add the optical traces or lines only where they bring you benefit, only where it's needed, where you really gain the most. The rest is remaining on copper. Then the optical tracing could be inside, or usually should be put inside on top, or particularly on top, maybe on top of the chip-to-chip connection of free space or separate to the PCB. That might allow you to do that. But this impacts least to the existing design. So really, the designers, they are tackling already with the space they have on the board or in the layers. So that might, let's say, bring benefit if the optical sits inside some of the layers. Then obviously we want the processing method to be compliant with the existing conventional PCBs. We need a pluggable connectors, we need a passive alignment, simple assembly, and high reliability long term. And these would be the, let's say, the smaller items. We have here the multimode waveguides in our case, a high dense form of those, some other more novel functions like the splitters, combiners, and overcrossings. That's a really, let's say, a more complex function that really gives you some functions that electrically you cannot do. And I think the next talk will highlight more on the design characteristics on these, and as well the benefits that we will gain. And obviously we need some coupling structures to get light in and out. This is just two potential and one a bit more practical. And this is, let's say, a demonstrative small-scale board that we fabricated many years ago, currently nearly 10 years ago. But anyway, we were able to fabricate optical waveguides for channels on standard conventional FR4 board. On top of the solder mask in that case, we utilized custom 12-channel transmitter and receiver on the other end, not the transceiver, but the transmitter and receiver. And we utilized the beam expansion concept to make the light coupling in and out from the VCSELs and to the photodiodes. We learned a lot. We tested different materials. We were able to show the data transmission chip to chip. And as well, we learned there, and now obviously at the TTM, we've been, let's say, this is our core technology or know-how. We fabricate the waveguides by ourselves. This is a, let's say, short glimpse on the waveguide fabrication process. We started on some sublayer or subcore substrate. We utilize, as was pointed out earlier, we utilize a photo-definable materials. We're able to make a patterning of each layer, if we will. Essentially, we deposit material, we cure that material, and then we go for the core layer. Core would be the optical signal tracing layer. We make essentially the same steps: coding, baking, exposing, developing. And then we have a tracing patterns. And these are the ones which carry the light. And then we seal the structure by adding an additional cladding layer. So cladding is fundamentally sealing the core around it at all sides. And then the board is moving to further steps to laminate it there with the couple layers. And if you look at the structures, how they look like after the patterning, here we can see obviously that all the layers, claddings, cores are being defined. This would be the bottom cladding layer, the PCB surface, the core traces with some alignment features, and the top cladding after being processed and revealing some pores in this case. And this particular cavity was formulated to passively align a chip, like in this case mirror chip. You can see the reflectance coming from the cores, and sealing the structure might be using a fluid or other material. As it probably was discussed earlier, how could this be made? It's very easy. These are photo-definable. You can really fabricate whatever shapes or functions or forms of traces and layers you need. And this is, let's say, another illustration of those kind of alignment structures that we use. Actually, we considered this is now the waveguide and the fiber coupled to each other with this cavity structure. This was earlier a job that we were developing for reliability testing, because the online testing, you might want to fibers to be nicely sitting and joining, and then you can do your testing and measure your waveguide performance in situ online. But anyway, so the passive alignment structures that you can fabricate within the core are flexible, very flexible with these materials. And regarding some of the, let's say, waveguide features that we've been fabricating, let's say earlier, these are not very new pictures, but anyway, showing, as we said, we currently work in the multimodal side. So this is an illustration of 25, 50 micron, 70 micron waveguide cores, 25, 50, and 75 micron with a pitch of coming from 100 to standard 250 micron pitch. This shows that we are able to easily control and modify the spacing or the pitch between the waveguide channels. Here coming to 50 micron spacing or even a 30 micron spacing. So considering that this 30 micron spacing is used with a 25 micron line, which design I just do not have here, would give you the 62.5 micron pitch for the outcome. And considering that this was the, let's say, the waveguide and the polymer waveguide formulation process, it's not the whole story. So when you try to and will to add those optical traces, part of the PCB, there are various other items. So this is just a, let's say, glimpse and simplified picture of a, I think, two-layer process: inner layer imaging, etching, inspection, oxide treatment. Then you add your waveguide layer into that particular board stack. Then you do your lamination, and there are various other processes: drilling, metallization, outer layer imaging, plating. And considering the very high layer count products, we may have multiple laminations, we may have a multiple sequential imaging and plating steps. This just highlights that there are actually, besides that fabricating a very nice performing channels, you have to be able to handle all these remaining steps and sustain your optical waveguide performance to be able to provide fundamentally a product which is capable of transmitting light inside. So this is now the fully built electrical optical PCB and some transmission shown in the corner. And this would be, let's say, the more recent type of products that we have been looking at. Usually these cases are like, I'd call it a product emulator. This is an existing product, and a customer would like to know what kind of changes he or she has to do in his design when he is considering adding any optics into it. That really impacts now not only let's say some drilling locations, maybe some, as was highlighted, the via structures, plating through holes, layer designations, or adding a different layers, but various other impacts. And this is critical to know up front. We need to know up front and be clear what the impact will be into that final design before we consider taking it into a product level. So in this particular case, the board thick was fairly thick. It was quite large and had 20 copper layers and this one optical layer inside. So some of the key performance parameters obviously needs to be characterized and measured, including material loss, waveguide propagation loss, bending channel losses, bending losses, crossover losses, and coupling losses. These are the critical, let's say, performance metrics that the designer will need when he considers that I'm going to make an optical, let's say, routing in my circuitry. Usually the chip-to-chip links or chip-to-edge, they're not straight. So you need all these components to make a design rule set and to be able to really make a circuitry sign out of the waveguides. And this would be for the waveguides and as well a lot of other parameters with the terminated connectorized channels as well. Then this is just looking at the physical side of the waveguide quality. As I said, many process impact items needs to be looked at, and before that, one of the physical key characteristics would be the sidewall or the wall roughness. The requirements in the copper side, when you fabricate today the high frequency 25 gig copper signals, the factories complaining already the dimensional tolerances, the surface roughnesses that they have to achieve, but they, let's say, not have a clue when we come to optics that the requirements are really on a nanometer range, the micro roughness or local roughness or the macro roughness around the board. So this really indicates a very smooth waveguide quality that can provide you the almost intrinsic material loss that the materials are able to provide, and a bit some waviness, not so perfectly imaged waveguide. But fundamentally, this is a glimpse of a scattering loss impact to your loss if your wall roughness is changing. So it's quite rapidly increasing loss depending upon your sidewall quality. And this is the loss measurement setup that we have in the laboratory. And there's one of our board, 30 centimeter, 40 centimeter straight waveguide with the output beam coming out. Then fundamentally, you use, of course, a source of your particular wavelength. In our case, it's 850. You have the micromechanical movers. In this case, this is a short sample, but now it's looking more like this one. It's a dark area, and you might want to put the, let's say, motor scrambler by wrapping up your fiber first and then launching. And having said this, I think just go directly to the details. But so obviously we have been as well focusing on significantly on the measurement itself. It's really, as you as an optical engineer are very well known, that the launching detection conditions clearly impact your measurement results that you're looking at or the data that you're obtaining. So considering that this is the one critical performance parameter of the waveguide, if fundamentally the transmission loss of your channel, how good your waveguide is. You would like that the testing is to be done in a manner that it's let's say agreeable. So there is an ongoing standardization activity at IEC Group which specifically tries to point out this dilemma and document that we need to, everybody in the industry doing this activity needs to perform the measurements in a formal way, at least document that if they are not using the same particular method. So that's an ongoing activity as well. So the actual data shows that the loss in these waveguides with the measurement setup that we use, particularly is scripted here, provides us as reasonable low loss numbers. So for these particular polymer waveguides, these represent, let's say, state-of-the-art in that field. So we are very happy to see this is a green light picture of a transmission through the waveguide core of 20 centimeter long waveguide. As been said, waveguides, when they are photolithographically patterned and imaged, we can do various items. So this is something that fiber or fiber routing cannot do. So the overcrossings with let's say fundamentally an angle that you would like to do, limited by the design rules that and performance that we are going to look at it. But essentially, any form of integrated component that you might want to add is feasible and doable. And this is the panel that we fabricated those particular waveguide structures and some cross sections of the waveguides as well. So a couple of words for the coupling, light in and out from the waveguide. So having the waveguides fabricated is good, is fundamentally needed, but you need to couple that light in and out, and this has been tackled by various solutions. And this is just let's say 3 categories of solutions based on a beam expanded approach without micro-optics, having a laser sitting very tightly, closely to the I/O, or even, let's say, butt coupling or direct coupling source or fiber to the waveguide without any beam turning. And in the earlier project, we as well concluded that a lens-based or expanded beam-based approach provides you largest, let's say, assembly tolerance. So that's a very easy concept to approach. So that's let's say the usual case as well in many implementations. In a chip-to-board coupling as well as in the waveguide to fiber couplings. And this is a bit more recent, our work within the Foxtrot project, where we actually showed another type of, as well based on a dual micro lens component and part of the midboard connector development. So we are providing a 90-degree light bending using a micro-optic component sitting inside the board. And this is just a red light illustration. And the work to improve this as a really a pluggable connector solution is ongoing. And this was let's say, demonstrator that we as well had this 90-degree mid-plane connector as well as the in-plane edge connector. We showed a white. Sorry, I'm really exceeding my time. Yes, an in-plane connector. We showed a live video transmission through the optical link coming with the fibers and through the polymer waveguides to the computer. And that was 2 channels used for the video transmission, 2 channels shown for red light. So out of those 12 channels, we used 4 for that one. Okay, very quickly then, some experiments we've been doing earlier. So are there very novel techniques to couple or formalize micro mirrors to the waveguides, couple light in and out? We've tested and shown 45-degree mirror fabrication. We've shown curved structures providing an optical function that would instantly not only turn the beam, but as well limit the beam for coupling light. But these are more experimental, so practical solutions usually stay on the connector side. So now a significant amount of work is being done at the Foxtrot project, where we develop multiple waveguides and interface solutions. And this is the first prototype that was highlighted in parts earlier slides, and will be talked more details in the, let's say, incoming sessions. And this was already provided in a Koby's presentation as well. So we are really, let's say, making a very challenging 16-layer router board catering the Compass COS routers, and it's going to be very challenging in many ways. And we hope to receive the results here to be shown. This is just a glimpse of the board structure itself. It's a complex as it is. So, quickly summarize potentials of lower power consumption, high channel density are the key drivers. Manufacturing is challenging but feasible for these optical waveguides, out-of-plane couplers, and routing components on PCB, even on a panel scale, and let's say fairly, low-cost manner. Coupling structures, connector solutions, optical engines are available or in development to provide end-to-end optical links, and for commercial viability, we need a supply chain across the industry, cost performance comparable, and clear product roadmaps and standards for the interfaces, construction, and testing procedures. Now I would like to thank you and have a question.
Yes. I would like to ask a question regarding the mirror, the one that you have between your pixel and the optical waveguide.
You recall the page?
I guess, yeah, this one.
This one?
Like the after this one.
After this one? Okay.
How do you fabricate them?
This is something I have not, let's say, talked too much about. So this is something this is not a, let's say, there are several ways to do that. Grayscale mask lithography or a proximity shadow lithography or something that very elegant. We have to, let's say, publish more to tell details.
And one more question regarding the tolerance of the classic alignment guiding space.
Mm-hmm.
What's the mechanical tolerance?
Oh, that's very good. So in a range of, let's say, micron. Because those are really these tactical alignment features that we showed. I apologize, terrible with this one today. For the fiber or for the for this one, if we look at these particular small features, or these pedestal or rails, or in the next page, within the same step as the waveguide. So the accuracy for this to this, or the dimensional stability is very good, within a micron range, or even less.
Have you looked at sort of the optical line card going into optical backplane and those connector issues, or you're just looking at sort of the single board, a couple of chips connected with an optical trace, and then sort of a fiber between those?
Yeah, yes, this is a good question. There are a lot of, as we started with the schematic cross-section, everything polymeric embedded. Let's say, I would say that if you have, various implementations can do. So if the link budget is enough, we might do that. Till so far, it has been shown that fibers are better for longer links, like in plane connections. In various cases, if the backplane design allows, then the links itself are not more than, let's say, 30, 40 centimeter. And if you cut that total, you are reaching that 1 meter link. And with the termination with the connectors, I think the budgets are not that large for going, let's say, consider 25 gig power consumption going budget. So in that case, it's going to be hybrid. If it's still, let's say, if you have a 12, 15 dBs budget, you might be able to do that.
Any more questions?
Yeah, Marika.
Yes.
Is there any constraint for you to step up on 18 by 24 inches? Because it's over there, you have 11 by 12 inches. Is there any constraints on the applicability of the material, of the polymer?
Going for
Can you do doppel glazing, or is that a problem?
Fundamentally, no, but we are not seeing the, let's say, the need for that. I'm not targeting the very large full format panels. I'm really seeing the links, chip to edge, less than 50 centimeter, or backplane connections in the same range. We are really satisfied with what we have now.
Yes.
I saw most PCB boards, they only have one layer of optical casing.
Could you please talk a little bit louder?
Okay. I saw on your slides most waveguide is only on one optical tracing layer. And for you, do you have a current technology can support you to make multiple layers to increase the density of channels?
Yeah, and what we've seen, let's say, various groups reporting. IBM showed earlier 4 layers or 2 layers today. We are working on that direction. We have shown 2 layers, not in this presentation, and let's say not coupled to the connector, so functionally working on multiple layers, not yet. But yes, we are particularly, for instance, in this Foxtrot project, working on that.
Okay, thanks.
Okay.
Do you have the transmission curve for that meter?
Do we have a transmission
curve?
curve?
You measured the transmission curve.
Not in this cut. I have a reflectance curve, transmission curve, only for that mirror. Yes. It was a high reflectance code, and actually we coded that, metallized that later. But so I have 2 transmission curves or reception curves for the component, and then measured for this particular wavelength after they built.
Okay. There are no more questions.
Okay, thank you very much.
Now we can proceed to our last talk that will be given by Richard. Okay. So Richard will talk to Optical Circuit Board design. Show you a last design of Optical PCB very, very soon.
Is all that coming first?
Hello, everyone. For those of you who weren't here for the first talk this morning, my name is Richard Pitwon. I'm lead photonics technologist at Seagate, and I lead the Photonics Research and Development Group responsible for embedded optical interconnect. Now, this is basically the second part of my talk. And this morning I talked extensively about data storage systems which are optically enabled. Today, now in this talk, I'm going to talk about optical circuit boards. Now, this follows on fabulously well from Marika's talk, where she gave actual practical examples of the challenges you face when putting this in a proper PCB environment. I'm going to give a more basic talk about the design rules and considerations that the PCB designer himself must take into account when he's designing optical waveguides. This is after optical PCBs have been proliferated. And then I'm going to look at the route to adoption, that is to say the commercial barriers that exist to the maturity of this technology. So what challenges must be overcome in order for this optical PCBs to be commercially proliferated. And finally, I'm going to talk about international standards activities. Doesn't sound so interesting, but it is quite interesting, because you need international standards to be in place for a technology to be really proliferated. So apologies, the first few slides are the same as this morning, but it's just to go back. This morning I spoke about data storage technologies, and I touched upon collaborative research activities. Today I'm going to talk about more advanced research and innovation surrounding optical circuit boards and standards activities. Now, as I showed this morning, you have this trend of migration of optical interconnect, where you have optical transceivers first on the card edge, now migrating to mid-board transceivers, which you've seen examples of, and mid-board transceivers with connections to the front face here or the back plane. And this lends itself, this is important, the mid-board transceivers, because this is the first example of optical interconnect technologies really, this is the first example of optical interconnect technologies really migrating, penetrating into the box. And so, although today you have mid-board transceivers which are fiber-coupled, the next step for this is to have them put on a substrate which is an electro-optical circuit board. So a circuit board with copper channels for power and low-speed signal communication, and optical channels for all high-speed communication, and coupling elements to this. And here are examples that we've seen before: fiber, polymer waveguide, and glass waveguide. And indeed, Lars Brusberg from Fraunhofer IZM will be giving a talk about the glass waveguide technology later on. Just a quick overview of what I consider to be the classical methods of optical circuit board fabrication. And I love animations, so I have to squeeze these in. The most traditional, I think, the most reliable technique is photolithography. And it's all based on the idea of having a polymer which responds to a curing influence. Either it can be baked or it will be subjected to UV light. And the UV light breaks the bonds and reorders them, so you get cross-linking. And this causes a change in the molecular density, and an increase in molecular density causes an increase in refractive index. And if you can do this selectively, you can create waveguides. So let me show you what I mean. You take a substrate, which could be a PCB with many copper layers in it. You take in liquid form, a lower index cladding polymer, and you blanket cure it. You cure it, it hardens. You might have to bake it sometimes, depending on the material, but you cure it and it hardens. Then you take a higher refractive index polymer, spin coat it or just deposit it in some uniform way, and then in order to selectively cure it, you can use, in this case, a photolithographic mask. You cure it with UV light through the mask, and that exposes only certain areas of the liquid polymer. It cures those areas and leaves the rest uncured. The uncured bits can be removed by washing or developing in a chemical solvent. And then typically you cover it again with a lower index cladding and then cure again so it's hardened. So there you have a completely covered set of waveguides. Another technique more popular at the moment is laser direct writing, which is more promising. Laser directed writing starts the same way. You have a lower cladding, which is cured. Then you deposit your uncured core cladding layer. But in order to selectively cure the structures, instead of using a photolithographic mask, you use a UV laser beam. And it can be, the beam can be shaped to give you optimal profiles, but basically you just write out the structures you need. And then again, you chemically etch away the uncured parts to leave the core structures that are critical to waveguiding. You cover it with a lower index cladding layer, and then you cure it again. This is a less traditional technique, but it is favored for some single-mode waveguide fabrication approaches. UV embossing. In this case, you have a lower cladding again, you have your core layer, but you take a transparent stamp. The stamp has itself these little, is a mold with the waveguide features you want. But while this is still in liquid form, you press this into the uncured liquid core layer, and then you cure it through the stamp. It's transparent to the curing radiation. Usually you'll have a release agent there so that you don't damage it when you're pulling it back up. But you pull it away, and that leaves these molded, cured structures. And again, you cover it for cladding. Photo dressing. This has been approached in various different ways, and usually it involves monomers, which are the singular units of the polymers you're using. You can selectively expose a special blend of polymers and monomers with either a photolithographic mask or a UV laser. But what happens is the areas which are exposed to light, it stimulates a diffusion reaction. And the diffusion reaction basically gives rise to either a change in molecular density for the refractive index, or you're dealing with a blend of two components. One is higher index, one is lower index, and then they separate in a certain way to create your waveguides. Now this is interesting because this gives rise to graded index waveguides rather than step index waveguides. And step index have the problem with dispersion. Graded index have been basically the holy grail for the last 10 years. Details on this technique will be given by Takaki Ishigure tomorrow in the first talk. I strongly recommend you attend this talk. He's going to talk about this technique and another technique, a very innovative technique for creating graded index polymer waveguides, which I won't cover here. And finally, one other thing is multi-photon absorption. This is where you take advantage of non-linear effects. What happens if you take a curing beam, and if you use a high NA lens, you can focus it to a point where you get very high intensities. And only in the area where the intensities are very high can you have the effect where multiple photons can be absorbed at the same time, effectively equivalent to an integer multiple of the photon energies. This doesn't happen here where you have relatively low photon densities, but here, only in this spot, do you get photon densities sufficiently high to stimulate this nonlinear reaction. And this gives rise to a cross-linking reaction only at the focal point here. So this is good because you can have a block of material, but you can create a waveguide anywhere in this block of material. This has been done in glass with Optigrate, which is a UK company. You can do this in polymer, and this has been shown by one of the Fraunhofer organizations. And again, you do the same. You can move it to write the pattern. So those are some common techniques for making waveguides. But when the designer himself has to look at what's necessary to make optical waveguides, there are various things he needs to take into consideration, various rules. We need to know about the loss mechanisms of a waveguide, and there are many. First loss mechanism is scattering loss at the end facet. End facets are usually quite rough. Usually you have a free space situation because you have say an expanded beam coupling element, so this has to be free space. It's not convenient to put refractive index matching on, so you will get scattering losses. You have absorption loss. The material itself absorbs the light. And the largest loss contributor in the waveguide is transition bend loss. When you move from one radius of curvature straight to a smaller radius of curvature, you get a change in effective NA. And the larger this change, the more you get a kind of spurt of light loss. The modes that can no longer be supported are just lost. And this is called transition bend loss, and this happens at the junction. If you've seen pictures of S-bends, waveguide S-bends, you usually see a big spurt, so right at the inflection point. The inflection point has the largest change in radius of curvature. That's what it is. Also along the bend, because the modal energy is concentrated on the outer edge, it's more susceptible to the sidewall scattering roughness. So you get scattering along the outer side of the bend. And the sidewall is, and this is emphasized here, you have a rough sidewall. Even though it's maybe 10 nanometers or something, it's still quite rough, and you still get some scattering. And you have crossover losses as well. And again, Fresnel and scattering losses at any boundary in and out. So let's look at waveguide crossovers. Worked on by UCL in collaboration with us a few years ago, was looking at putting into place some design rules. And in fact, my colleague Kai Wang, who's here today, he was working for UCL and he did a lot of work on this in this area. Crossovers are one of the benefits of having optics. You can, unlike copper, you can have channels crossing each other over. But what's the optimum crossover angle? 90 degrees is optimal. But what other channel? What range of channel crossover angles are possible? Here you see a picture where they're quite steep. Oh, sorry. There we are. So here you see a little animation there. Now, can you achieve crossover angles like this? Possibly. You have to take into consideration one thing. The direction in which the data is traveling. If the data is traveling along the long axis, sort of roughly parallel, then you'll get large crosstalk and probably unacceptable crosstalk on both channels. However, if the designer knows in advance what direction the data is going to be traveling, he can tolerate this angle as long as the data is traveling in opposite directions. So by knowing the direction of information transit, that gives you far more flexibility with crossing angles. And that's a very important outcome of this study. Bend radius is very important because of the aforementioned transition bend loss problems. Smaller bends means more loss, and bend transition loss depends on the change in what we call the effective NA of the waveguide. And you have bend scattering losses, which depends on sidewall roughness and the radius of curvature. There is crosstalk between waveguides, and you find that step index waveguides, which have a lot of modes, especially a lot of higher order modes, are also more susceptible to crosstalk because you will have greater scattering from here. So this requires you to know, depending on your material, what's the minimum distance you can have between two waveguides. And also, if you're on a bend, do you have to move it slightly further apart because you expect more loss, etc.? All these things have to be taken into account. Numerical aperture is very important. This is a numerical aperture is based on the refractive index, the difference in refractive index between core and cladding. And it's determined by your choice of optical materials. And one very important parameter is the tunability of optical materials, as the tunability of the refractive index. You want to have as wide a tunability as possible to give you more control. Larger differences between core and cladding and step index waveguides mean you get more dispersion because you can get thousands of modes propagating. But it means you can get higher optical confinement. So that's a trade-off. You can get out of this trade-off zone completely by moving to graded index profiles. That way you can achieve tighter bends and you have less dispersion because you have a graded index profile. And the important thing here is that you have a high enough delta. A lot of people in the past have made graded index polymer waveguides, such as by two-photon absorption. But the problem was the delta was so small that they still were getting a lot of losses on the bends. So the combination of a graded index profile and a high index delta is absolutely ideal. And again, I direct you to Professor Ishigori's talk tomorrow morning to learn more about that, because work in Japan in this area is extremely advanced. I'd have to say more advanced than in Europe, and it's definitely worth listening to this talk. Also, waveguide routing considerations. Never in a real situation will you have a waveguide input which is collinear with an output. This is highly unlikely. In a real board, you're going to have lots of electrical components. You'll have lots of penetrative features. You'll have lots of wires. You'll have through holes or connector features. You have to dodge these. There are features that penetrate the board which are inevitable. You have to dodge these. That means you have to have the versatility to make quick turns. And when you have lots of waveguides, of course, waveguides will be crossing each other at some point, so you have to be aware again of the crossing angle. So you have to turn to make sure that your crossing angle falls within a certain range. So these are all things you have to take into account. So everything has a knock-on effect on everything else. So to summarize, what I see are the challenges to commercial proliferation of optical waveguide technology. First of all, there's the material composition. As I said earlier this morning, optical polymer materials have made incredible leaps and bounds over the last 10 years. 10 years ago, they would become yellow in a few years, which makes them unusable. Now you have fantastic materials like the Dow Corning materials, excellent properties. Polymers still tend to be very transmissive, most transmissive at the shorter wavelengths, and are quite absorptive at 1310 and say 1550. But even there, advances are being made in materials to give you less absorption. Connectorization is the major challenge. How do you reliably connectorize optical waveguides on a circuit board? How do you put, say, dozens of optical connectors in a high-yield way? This is difficult. Numerical aperture, tunability of refractive index. Again, material providers have made excellent advances in this field, and that has a knock-on effect on minimum bend radius. If you're designing a board, you need very tight bend radii. Otherwise, it's not realistic. What can be achieved today is simply too large to be practical. And refractive index profile, ideally, you want a graded index profile. And versatility with crossovers. Now, here's an electro-optical circuit board we developed a long time ago, actually, but it had polymer waveguides, and here you can see one of the waveguides illuminated with red light coming to an interface. We developed a special connector. This was an active backplane connector, so it had a transceiver and a connector mechanism all in one, and this allowed a daughter card to plug directly into the waveguides. And this was also one of the first examples of a dual-lens coupling interface, what we know now as expanded beam. And this is important because in a real environment, such as a data center environment, you will not have the luxury of cleaning the interface every time you plug in. And there will be dust, because it's a forced air environment. It's inevitable. Expanded beam is great, because by expanding the beam, you make it far less susceptible to contamination. So if there's a little bit of dust here at this point, then it blocks a small fraction of the beam. If it's at this point, however, then you're blocking most of the beam or all of it. So that's why this is important. Connectorization, as I mentioned before, we needed a receptacle on the board, and this meant we needed a passively alignable optical interface. We developed a technique a while ago, which is a passive alignment technique. It involves building, again, an undercladding layer, a core layer. In the core layer, we had a group of waveguides, but we also created extra waveguides in the core layer on either side. Now, these waveguides served as registration features. We selectively removed the upper cladding so that you expose the outer facets. And because these are made in the same step as the waveguides, they're very accurately positioned with respect to the waveguides. And so we could create a high-precision piece could mechanically, because these are multimode waveguides, you could actually feel it, passively align with to the waveguides. And we got an accuracy of about plus or minus 2.5 microns. Accuracy with that, which is more than enough for multimode waveguides. And here on top of that, you put an expanded beam solution. And that's what this is. Another aspect we've been working on with UCL, actually UCL have been spearheading this. This is how do we reduce end facet waveguide roughness. And they were looking at routers. The milling routers. This is how you mill PCBs. And they're looking at parameters of rotation speed versus translation speed, and they're looking at different combinations of them. And they had this kind of optimum area point at which you can get the smoothest facet without the need for polishing. We at Xaritex are developing another technique, which is low cost for end facet roughness reduction, which I can't go into at this point, but it's something we consider very important. But bend losses, transition bend losses, as I said before, are the largest contributor to loss, especially if you're going to have a lot of bends in a waveguide. We have developed a technique for completely eradicating transition bend loss in simulations. The ability to fabricate such waveguides exists, but it's not something we've achieved yet, but we're working with partners to do this. But there is a technique, it's currently being patented, but it does, according to simulations, completely eradicate bend loss. It sounds too good to be true, so we're skeptical. But the results are very good. I'll end this by talking about standardization. I'll rush through this quite quickly. There are various international standardization organizations for conformity assessment. You will have recognized IEC. Laser safety classifications are based on IEC standards. IEC is an organization which we're engaged with. It's an international non-profit organization, and it basically creates conformity standards. This is the organizational structure. The important part for us is this, the management of international standards. Now, we are involved in Technical Committee TC86, and this involves all aspects of embedded optics, from fiber optics to transceivers to cables. We're in a special group called Joint Working Group 9. And this group is a standards group responsible for optical circuit boards. Very important. Optical circuit board standardization is an important prerequisite towards commercialization of the technology. That's why we're involved in it. Here you can see the distribution of experts by national committee. Japan has by far more experts than everyone else, and the reason for that is that Japan, this is actually born out of Japanese standards. Japan have been driving optical circuit board standards heavily, and are the key drivers here. These are examples of some of the standards documents which have been published, and you can find them online. I will talk about one standard which is in progress, something which is quite important to us, and this is about specifying measurements. When you have an optical circuit board, this is a problem which we've had for the last 15 years. When you have an optical waveguide sample and one person measures it, then another person, and then another person, they get wildly different results. And the reason for this is that they don't specify the measurement conditions. Insertion loss is based strongly on your source characteristics, on your launch conditions, more than everything else. How did you treat the input facet, the output facet? How did you capture it? These are all extremely important. Otherwise, quality assurance goes out the window. Results are meaningless unless you specify how you measured it. It has to be repeatable. So the purpose of this standard in progress is basically to provide a code. And this code is based on lookup tables, and this specifies your source characteristics, your launch characteristics, your input facet and output facet conditions. Do you apply oil? And your capturing conduit. And basically the standard involves lookup tables. You create the coordinates of this by consulting a lookup table to say what source are you using, what wavelength is it. The second one is launch conditions. What type of fiber are you using? Are you using fiber at all? Is it mode filtered? What are the launch conditions? Are they compliant with this or that? Then what do you do to the input facet? Do you apply refractive index oil? Do you image it with a lens? Same with the output facet. And finally, what fiber do you use to capture it if you use a fiber at all? And the idea is that forcing users to create this code means that it forces them to specify the measurement conditions sufficiently to ensure repeatability of results. So an example of deployment is this code here represents all of this information here. But it forces them, and that's very important. In conclusion, I'll just say that optical PCB circuit board technology has evolved considerably over the last 10 years. Design rules are important to take into account because we'll soon be at the stage where people will be designing these waveguides themselves. And there are lots of international standards activities pushing this forward. That's my talk. Thank you. Everyone wants coffee, yes. Yes.
Do you see any future in research of the materials for these polymer waveguides? Do you see this important, or you see this is something that is negligible? You don't need to pay any attention to this, and you think only to focus on designs?
I do see it important. There was a question earlier about where do we see the winner? Was it polymer waveguides, glass waveguides, or fibers? And I see there's a role for everything. Polymer waveguides I see as having a role for interconnect restricted to the enclosure. Not necessarily connected out of the enclosure, but board to board. I see that as a very strong contender for polymer waveguides because it's potentially very cheap, and once people like Marika, like TTM Technologies, can do this en masse, very interesting. And ideally, you have chips coupling directly to waveguides and talking to others. All the technology steps are there. It's just that, in my opinion, the one key challenge to overcome is connectorization in a mass production environment. Everything else is there. Materials are there, everything else. So I do expect to see that.
You talk about the crosstalk versus crossing angle. So when you change the crossing angle bigger than 90 degree, and so the crosstalk level will be reduced. So my question is, will the loss increase because the bigger crossing angle?
Yes, the loss on the primary waveguide will increase because more of that light is going into the other waveguide.
How big is that?
It depends completely on your fabrication technique, your materials. It varies so strongly. Excellent results have been presented by Dow Corning and Sumitomo Bakelite on crossing losses.
Okay, thank you.
Yes, because we are behind schedule, we are going to now proceed with the two last presentations, and then there will be the coffee break where everyone will be able to take a cup of coffee and go to the posters. Okay, so now the next speaker is Johan from AMS, and he will give a talk about Optochips and 3D system in package integration. Okay.
Good evening, ladies and gentlemen. Thanks to the organizers to have the possibility to talk here. My name is Jochen Kraft. I come from AMS, and I think I have to switch to my talk.
Do you have the presentation?
So I thought you have it here.
I don't.
I have it on a USB stick.
Which one is it? Is it one of these?
Okay.
Okay. Where is it?
Go down, please. Okay, this cup. Okay,
Where is it?
Well, just a few words about AMS. AMS is a relatively small ASIC company. We have about 1,300 employees, and we produce at the moment about 120K 8-inch wafers per year. We are about to increase the number of wafers to about 150K per year, and from our currently 0.35 micrometer technology, we are about to switch to a 0.18 micrometer technology. This is the outline of my talk. After a short introduction, I want to talk about the 3D integrated photodiode, which was a successful product with which we entered the field of 3D integration. Then a few words about our integration concept, how a photonic chip process flow could look like in the frame of this integration concept, then about volume manufacturing, and finally the conclusion. Okay, introduction. So I think this is a well-known chart, and you know all this headline more than Moore, and on the other hand more Moore. So while more Moore is just a straightforward decrease of the node, more than Moore is a sort of diversification. So in the case of AMS, I can say we have here, for example, SiC transistors. We introduced a epitaxial deposition of SiC transistors, which enabled us to have bipolar transistors with a transit frequency of 70 gigahertz. And this enabled us certain products that we could not do before. But now, when we entered the field of 3D integration, so this is meant by this arrow here, we are somewhere in between the field of system on chip and system in package. So we believe that 3D chips with TSVs will be a key innovation for us, for future products. Where are we in the field of the 3D market? So here we see 3D wafer level chip scale packages, which is more or less in the Asia region located. 3D integrated chips, where we also count ourselves, and 2.4D interposers. So in this definition, it is meant that 2.5D is an interposer without active elements. So in our case, in our products at the moment, we have the TSV through active devices. So this is on a common definition, so to say, a real 3D. We are here, still less than $10 million revenue, but a lot of other competitors in the field of 3D are even lower. Okay, here we have a study from Yoli Development from 2012, and we see us mainly in the field of MEMS and sensors. AMS is dedicated to sensor applications. Okay. On the other hand, well, these RF applications are located here. So in the field of 3D, both are rather small compared to areas like imaging, optoelectronics, or also here logic 3D or memory. Good. After this more general introduction, I would like to come to our product or products with 3D integration. So the idea behind it was especially a form factor reduction. So you can easily imagine if you have a chip with a traditional bonding compared to a chip with the TSV and a bump on the backside, which enables flip chip bonding, you have enormous reduction of the form factor. And in a second approach, where you have two chips, maybe also with different substrates, you can bond these both chips together, and again with TSVs and flip chip bonding gain a lot in the form factors. In addition, you benefit from the reduced resistance and capacitance, reduced power consumption, increased speed, reduced signal losses. So there are a lot of improvements, especially that will especially result in a cost reduction. Okay, now, as already mentioned several times, this is now a real product. It's a schematics cross-section of a product with which we started this 3D integration. And the idea here was we had two chips, a photodiode chip and a CMOS with an integrated circuit. And with this integrated circuit, the data that came from the photodiodes were processed. And before, as we have seen a slide before, these two chips were on different positions and needed much more space. And here we bonded the wafer with the photodiode, which was a different substrate, where we needed epitaxial material, which has advantages for the photodiodes, and then made an electrical contact with the TSV and had a much more compact solution. This was used for computer tomography systems, and you can easily imagine these are the photodiodes inside of this computer tomography system. And now 100% of the area could be used for the sensor itself, because the chip which was responsible for the processing of the data is sitting on the backside of these photodiodes. And the feedback from the customer was clearly he had a improved image resolution, which is due to less noise, which was originally not expected from him, because it was especially the form factor and the usage of 100% of the area that he wanted to benefit from. But this resulted then finally in a lower radiation dose that was needed for the patients and system power savings. The next part will be the integration concept. So in principle we have two approaches. One of these approaches was already introduced. This would be this kind of approach. You have two chips, a sensor chip for example and a CMOS. They are bonded together, and the TSV serves as electrical contact from one chip to the other. And a newer approach is like here. You have only one chip or one wafer. You have a CMOS application on one side, and then you enable by the TSVs bonding of this wafer from the backside. So instead of wire bonding, you have then a redistribution layer on the backside, and via these bumps you can do a flip chip bonding of this chip. And here we see a huge interest of customers who want to, who have already a chip in production, and now they say, okay, instead of having this chip with wire bonding in the package, we want to do a flip chip bonding. But we want to keep all the layout as it is. So the ideal situation was if we had to each pad where the bond wire is attached to a TSV from the backside, and then do the bonding from the backside. That's where we are working on. TSV last approach This means just that the TSV is done after all the CMOS and so on is finished. So we have to develop a TSV module itself, meaning the etching of the hole and the isolation, deposition, and metallization. Then RDL, this is the redistribution layer. Wafer-to-wafer bonding. Here we gained a lot of experience in the last 5 years, and there are quite a lot of issues with voids at the wafer edge, with treatment of the wafer surface, cleaning, and plasma treatment to enable the direct bonding and so on. Then wafer level bumping. Clear, that's the target where we want to go to. And optional post-processing modules is mentioned here. As an example, this could be, for example, a filter application on top of the CMOS and some photodiodes within the CMOS. This is how the TSV looks like. I already mentioned you have to etch a hole into the TSV. This is done with the Bosch process. Then you apply isolation oxide, metallization, and this serves as the electrical contact from the one side of the wafer going to the other side. So this here can now be either the metal one of the bottom wafer, or it could also be metal one of the wafer itself. What I have to mention here, we have a rather exotic approach. While most of the competitors have TSVs which are copper filled, we do hollow TSVs. So our TSVs at the moment have a diameter of 80 micrometers, and we use as a metallization tungsten. Tungsten has the advantage that the thermal expansion coefficient is much closer to silicon than in the case of copper. And this results in less stress and better reliability. So though we are quite alone, we still believe in the success of the tungsten metallization. Okay, so again, these two integration approaches and the process flow. So again, here you see this is the solution with the sensor and the CMOS. So I just go quickly through it. We do a CMOS wafer thinning, then the sensor wafer is bonded, TSV formation, isolation, oxide etch. This means this is the TSV processing, passivation, structuring, bumping, dicing, and automated optical inspection. This is now a cross-section of this TSV. You see it's a rather large device. And on the back side here, this is 20 micrometers left of this photodiode sensor, photodiode wafer. As this wafer is bonded with the direct bonding strongly to the lower wafer or to the second wafer, it can be as thin as 20 micrometer wafer because the mechanical stability is carried by this first wafer. And here you can see a bump which is connected via the metallization in the redistribution layer to the metallization in the TSV. This is the second approach. So we have only one wafer, which, as you remember, should be enabled to do a flip chip bonding by the redistribution layer on the backside and the TSVs. So the process flow in this time is a bond oxide deposition. We need also here a second wafer, of course, in order to have the mechanical stability. But this is only a temporary bonded handling wafer which will be removed afterwards again. Then when this handling wafer is carrying the mechanical stability, the silicon of our device wafer can be thinned. Here this is usually done to 200 micrometers, but 100 micrometers would also be possible. TSV formation isolation. This is again this TSV module, RDL deposition, passivation, handling wafer removal. So this is a new step, bumping, dicing, and that's as seen before. So in the first view, you probably would say this looks similar. Okay, the TSV is pretty similar, but this time we have here no second wafer bonded to the backside. So here we only have a thin membrane of about 6 micrometers containing the back end of the wafer. So here we have metal 1, metal 2, metal 3, together with the oxides which these metals are embedded in. And this looks quite unstable, but I must say we have produced such devices, and we have also feared that there could be some reliability problems. And after handling and inspection of more than 100,000 of these parts, there was almost no issue with cracking. So it is indeed surprisingly stable. Good. So now I come to the photonics, the reason why I'm talking here at all. I must say we are pretty new in this field. So we came to the photonics via the EU projects Helios and now Mirage and Foxtrot. And we try to adopt our 3D principle or process with the needs we saw in the photonics. So a photonic chip should, additionally to the electrical input and output that a chip can serve, also have this light input and output. And this means it needs some photonic functionality. And in our case, I mean, that's just a simple application now within this EU project. We add a waveguide to a silicon interposer. In principle, this could also be a CMOS run or a silicon wafer with CMOS functionality. This would not make a real difference for the TSV processing. Above the waveguide, we deposit metal 1, metal 2, metal 3 layers. And then this is now quite similar to what we do with our 3D integration. We add a first temporary handling wafer, which makes the stability for this device wafer, and we can thin it to 200 micrometers. In principle, the thinning can be done down to 20 micrometers. But of course, you have to consider that you have to handle the wafer afterwards. So a debonding is possible on our machine up to 50 micrometers. So this is the limit we have as a target in the Foxtrot project. With the support of this temporary handling wafer, we can now do this TSV module, Bosch process etching, isolation, metallization, and so on. And in addition, we open also the pads of this redistribution layer here. Then the second temporary handling wafer now enables to remove the first temporary handling wafer and enables further processing on this side, which mainly means that we also open pads on this side. So finally, we end up with this interposer, which have an interposer with grating couplers or whatever is needed, and we have the possibility to do a mounting of chips on both sides of the wafer, like here. And this is more or less our target for Foxtrot, to produce such a wafer with tiers on one side, and a driver, of course, and VCSEL and photodiodes, which can interact with the waveguide on the other side. So far so good. One problem now is, of course, the speed of the TSVs. We have now learned a lot about bandwidths and frequencies, and actually we did not know what frequency such a TSV can carry at the beginning of the Foxtrot project. So now we are working on this, but the problem is how to measure the speed of a signal that can go through a TSV. Because with frequencies in a gigahertz area, you always have the problem of parasitic capacitances and so on. So we do we put S-parameter structures onto the chip with this ground signal ground needles, which are especially shielded and everything, but still you can only do contacting from one side. So you always have to go through to two TSVs back and forth in order to measure something. And with this, we reached with the 3 decibel bandwidth something about 5 gigahertz, which is not enough for the targets of the Foxtrot project. But as I said, this is not the bandwidth of a single TSV. It's 2 TSVs and an additional metal line. So the second approach was now to measure, to have only 1 TSV. The signal will go straight on this side from port 1 to port 2, and this TSV is just a, so to say, a dead end, which can absorb energy. In this case, we come at least to 15 gigahertz. The red curve is with a substrate thickness of 78 micrometers. The blue is with a substrate thickness of 180 micrometers. So in principle, we expected that having only half of the thickness of the substrate would also result in only half of the parasitic capacitance, but actually there was not a very big improvement. Simulation that we performed before all these measurements is this, and here we varied the thickness of the substrate and also the diameter of the TSVs. So actually we have 80 micrometer TSV, and as you can see, if you go to high frequencies, it seems that only the diameter is important in this simulation. Good. So I think the time is almost over, so we'll go quickly over volume manufacturing. I just want to present here some measurements we did during the volume manufacturing, showing that the TSV processing is a stable process, because it was for us a new system, and we had, or we wanted to have a close look on this. Here, again, a cross-section of the TSV. This could be interesting. Here, the white line is the tungsten, which is the metallization of the sidewall of the TSV, and this is the redistribution layer making this contact here. Main parameters, since TSV is quite a simple device, the TSV resistance, a leakage to the substrate, and the breakdown voltage from the TSV metallization to the substrate, which is rather stable. And here the TSV resistance for this was still the 100 micrometer diameter TSV and 250 micrometer depth. We had a TSV resistance of 350 milliohm. It's quite high compared to a copper TSV, but it was sufficient for the application. Okay, and here from our quality department some investigations on TSVs where they did thermal stress and aging experiments. So, conclusion. 3D TSV technology opens new markets and applications, which we already see. Qualification under automotive conditions and reliable manufacturability of AMS open TSV technology was proven. New 3D integrated photodiode ICs with reduced footprint and improved performance are successfully running in volume production. And as far as we can say for the photonic chip, it is feasible. And we will see next year more, probably. Thanks for your attention.
Okay, good afternoon, everybody. My name is Kozyris, and I really feel like a fly in the ointment here. I mean, it's the only talk that doesn't contain a word photonics or optics. It's the only talk that may speak about the perception of a service provider. The service provider is GRNET, Greek Research and Education Network. So bear with me. I know that I'm the last talk I'm between you and the coffee break, but bear with me. I will try to give you the perception of somebody who is trying to build services. So, a few words about GRNET. GRNET is the Greek Research and Education Network. It's a state-owned company which provides infrastructures, services to the Greek research and academic community. So we provide the national and international connectivity to GEANT. I will briefly talk about this, and we provide infrastructures and services to the researchers, so we give them network, computing, and storage as a service. And of course, we promote the dissemination of ICT. Some numbers about our work. We interconnect more than 100 universities, research centers, and institutes, more than 15,000 schools all around Greece. So in total, we have more than 1 million end users. We have a pretty good network, dark fiber, more than 8,000 kilometers, DWDM technology with multiples of 10 gigabits per second, and the access to the universities is multiple lambdas, so we can have a light path from Aristotle University here to Athens for an experiment. The light paths are 10 gigabits per light path. And we have the international connectivity with the GEANT network, which is 30 gigabits per second. We operate the neutral internet exchange for Greece. We interconnect all the industrial providers, the service providers in Greece together, and we are offering cloud services with 3 data centers that we have in Athens and in Epirus near the Louros River. We have there a facility with containers nearby the hydroelectric plant, and this gives us some latency and some problems, as I will explain. So this is the kind of the situation in Greece. This is the network we have. We operate more than 8,000 kilometers of dark fiber, metropolitan area networks in Tekin, Athens, and in Thessaloniki, loops all around 30 cities. So all the network is protected, and the availability is more than 3 nines at the moment, and we can say 4 nines. And we have the network is operated by GRNET through an IRU with the incumbent operator in Greece, a 15-year IRU. So the next of my talk will focus on Okeanos, or Okeanos as we call it in Greece. It's an infrastructure as a service cloud, and I will mainly talk about the challenges we had and some figures to give you food for thought about the requirements of a small service provider. So why we called why we named the cloud service in Greece Okeanos? We know the cloud is something vague, something which is not something abstract. So Okeanos is the Greek word for ocean. I'm not sure if you know it, but the 50% of the oxygen on Earth comes from the oceans. When we were trying to find a word to name our service, we wanted to show the abundance, to show that we have a lot of resources. So we came up with the word Okeanos because the oceans contribute more than 50% of the oxygen on Earth due to the phytoplankton, due to the small plants that they have on the surface, and they make the oxygen. So the oceans are an abundance of energy and life, so our cloud, we wanted to be like this. So how we started? We started 4 years ago. We designed a cloud service with the ambition to be something like the Amazon cloud service. Are you familiar with the Amazon Web Services? Has somebody started VMs with Amazon? Okay, a few of you. That's fine. So let me give you some numbers. We have more than 800 users. We have more than 9,300 VMs currently virtual machines which are currently active, and to show how stable the platform is. We have more than 300,000 VMs started and stopped the last 3 years, and more than 82,000 virtual LANs spawned so far. So we start and stop the LANs based on the requirements and the needs of the users. So what kind of service we offer? We offer different virtual machines with different flavors. More than 340 flavors are available, and the typical one could be something like 4 cores with an 80 gigabyte disk and 8 gigabytes of RAM. So in the figure here, you can see the uptake. When we started it, immediately the people started requesting resources. So this is 1 year old and shows how fast was the uptake of the needs of the user. So what were the goals of producing producing Okeanos? We wanted to create something which is production quality. I mean, we are a service provider, and nobody wants to lose a VM and lose his data and lose his work. So all the VMs, every single VM is a stable VM. We haven't lost a single VM 3 years now. We wanted to scale up to thousands of users and thousands of nodes and tens of thousands of VMs. And the numbers, although we are a small to medium provider, show that we need a lot of bandwidth and very, very low latency, as I will explain later. So our VMs are persistent. Our VMs are not cattle. I mean, they are pets. They are our own VMs, and we want our work to be there and be persistent. And another issue that we wanted to take into consideration is that we wanted to be based on commodity components to lower the cost and be able to not to lock into a single vendor, but be able to scale up without thinking about which vendor should be the next one to provide us with equipment. And of course, all this should be with low administration costs, managed by a small team of experts, service operators. If you're familiar with the cloud offerings, which still exist out open source ones, we had Eucalyptus, which is now not so fancy. We had CloudStack, OpenNebula, and OpenStack, which is perhaps the most famous cloud stack for building IaaS clouds. We believe that even OpenStack is an evolving system. It's not so stable. I mean, it's very difficult to find a very big installation with tens of thousands of VMs based on OpenStack. So there are no turnkey solutions. And there were no turnkey solutions back 3 or 4 years ago. So our approach was to, since GRNET operated 10 years ago data centers, was to keep all the stability of the data center with the infrastructure, with the servers, with the interconnects. I forgot to say that the interconnect we have in our data center is a 10 gigabit Ethernet for all our servers. So we wanted to keep the stability of the underlying infrastructure, and on top of it, to build our software and offer cloud services. So if you see the what kind of approach we followed, it's on the left side we have the OpenStack, which seems like a silo of software on top of hypervisor and virtualization software, and on the right side it's our approach where we have our own software stack. We keep the compatibility in the interfacing between third-party applications with the same API, and we use for the cluster management and the node management, for the data center management, well-behaving technologies from Google. I will elaborate on GRNET a little more later. So the software that powers our cloud is called Synefo. Synefo is the Greek word for cloud. Okay, we couldn't avoid using cloud as a word. It's an open source cloud software which is written in Python, and if you see the development, it's a heavy work. 3 years now with a lot of releases, and all the software is available, and as I will show you, there are some data centers outside Greece and Europe that use them. So what are the components that we have? We are based on open source components. We have Cinefo, which is our own homebrew software. We use KVM, which is well known from Red Hat now, and we use GRNET by Google. So GRNET is a cluster management software which is developed by Google. It's open sourced, and we heavily contribute to it. So what are the main features? We have persistent virtual machines. We are based on commodity hardware. With 3 simple clicks, you can start a VM, and it's very simple to operate. You can add more volumes, you can add networks, etc. So, under the hood, in the heart of the 3 data centers that we have, we use GRNET. GRNET is a cluster management tool made by Google. They open sourced the software in 2007, and by then we started contributing to them. So at the moment, 8 Greek engineers are working with Google, and we help them develop and improve GRNET. If you want to see more about this kind of software and how Google IT is operating, how Google IT is keeping pace with Google's growth, GRNET is a tool that operates all the internal IT. So you can see how they manage thousands of servers with GRNET. And GRNET, we are proud that we have a strong collaboration with them, and we are the biggest external contributors for their tool since 2007, and our data centers are based on this tool too. So this is a presentation by Thomas Limoncelli from Google back in 2012 in the large installation system administrator conference, where they explain how the GRNET can power a data center. I will focus on things that make a service provider scalable to tens of thousands of machines and to hundreds of thousands of users. So if you see from Gartner, the magic quadrant they have, these are the service providers, well-known service providers like Joyent, SoftLayer, etc. And you can see that Amazon is far beyond on the top right corner, more stable, more scalable, more able to execute than any other provider. And Amazon is able to scale up to these numbers, to millions of VMs, because they have their own technology and they are based on commodity components, and they have a very, very low cost for their servers. So how we scale up? As I said, it's more software, but we need the infrastructure underneath to help us. I mean, it's a software-defined solution. A cloud is a software-defined thing. I mean, there is no storage area network. Everything is powered by a 10 gigabit Ethernet, but it's not enough. And it's not enough to say that we will power it in some years with 100 gigabit Ethernet. So the storage is thinly provisioned, and there is no local storage. So imagine that you are hosting tens of thousands of VMs in a data center. Let me say hundreds of thousands of VMs. And each VM has 100 megabyte per second need for its own local storage. So you make the math. If you do the math, you will see that we need terabytes per second bandwidth. And that, of course, how we make it. I mean, we have a distributed object storage scheme. So in parallel, we access many storage servers, and we have a technology that no VM has local storage. But even with this technology, it's not enough to give to every VM the bandwidth it needs. We have the need of evacuating a node which contains 50 or 70 VMs, and we don't want our users to see the difference between migrating a VM from a data center to another data center. So we need bandwidth and we need low latency. So what are we doing now? I mean, we are doing it over Ethernet, but we cannot take a VM from a data center to another data center without making the user noticing the difference between this migration. When we have VMs that they have 64 gigabytes of RAM, and we copy pages from one container to another container, so this is not only an issue of bandwidth, it's only an issue of latency. So, I mean, we are using 10 gigabit Ethernet, 10 gig Ethernet, but it's really the roof in our performance. Let me say a few things about our storage. As I explained, it's a distributed storage system. In order to have an aggregated bandwidth of terabytes per second, we are using tens of storage servers, and we distribute all the volumes, all the objects to the different servers, and so the volume of a single VM is made of objects from different servers. That's how the aggregated bandwidth comes to hundreds megabytes per second for all the VMs. And of course, it's the only solution that we have in order to provide everybody with the bandwidth. So, in essence, how fast can we provide 100 Windows 2012, for example, servers? I mean, if you have an experiment, you're making a simulation, and you want 100 servers, 100 VMs, how fast can your service provider provide them to you? You need days, you need hours, minutes, or seconds, as it's in our case. So we're providing in less than a minute 100 of Windows 2012 servers to each of our users. So how we scale, which is the secret sauce, we are simple. As I explained, everything is commodity, everything is open source. We take the most simple things, like the Legos, and we construct a big IT infrastructure. How we do it, the building blocks, as in Legos, are the compute, the VM, the network, the storage, and the firewall. So we try to couple all together, so every user selects which kind of resources he needs to assemble a larger three-tier architecture. So, for example, if we want to make a three-tier architecture, we take the building blocks of our cloud platform. We put a VM here, we are making a virtual LAN there, we interconnect two other VMs with their own volumes, and then with another private network, two other database, for example, servers with their own storage. And all these are simple blocks from our platform. So this is the kind of resources that the user can use. And let me show you some screenshots of our platform. Here you select the number of CPUs, the memory size you want, the disk size, and the storage, the kind of storage. We have pretty many flavors of operating systems, Windows and Linux flavors. And here you can see how your machines are being seen in the internet, interconnected and in the local with two IPs, IPv4 or IPv6, because all the data center is, all the service is IPv6. So this is a screenshot from the landing page of Okeanos. You can see the numbers. The active VMs last night were 9,141, and the number of spawned VMs. Let me give you some info about who has our own software. Apart from GRNET, ZEANT, the Pan-European Research and Education Network, I'm sure that many of you have academic credentials that can use the Okeanos Global, which is the European cloud offered by Okeanos. So you can go to Okeanos Global, as I will show you in a minute, and you can use your credentials from your university or from your research center to take VMs for 6 months. This is the Danish Infrastructure Cooperation in Denmark, which has a similar service like ours with Cinefo. There are data centers in the private sector, in companies in US and in Germany that they are using our own software. There are installations in Australia, in South Asia, etc. So this is the offering that ZEANT has announced for our cloud, Okeanos Cloud, the Okeanos Global. So if somebody has credentials from an academic institution in Europe, or, for example, you are using the DuRoam facility here in the room, with these credentials, you can go to Okeanos Global and start your own VMs in a couple of seconds. This is the Okeanos Global screenshot, the same, that it's just a difference here, and you can see the address you can use for starting your own VMs. Some events for the Cinefo software, FOSDEM, LinuxCon, and CEF Days. Some pictures about with our data center. This is situated in the Ministry of Education. Some rooftop pictures from the chillers and the machines that produce electricity. More pictures. Okay, so you can see more to the software page, cinefo.org, to the service page, okeanos.grnet.gr. You can have a quick tryout either to the demo.cinefo.org page or using Okeanos Global with your academic credentials as member of the ZEANT community. And the presentation is available to the link and also to your USBs. With this, I conclude my talk, and I thank you very much. I guess the coffee is hot still, so it's okay. We have two contradictory goals. I mean, the one goal is to keep commodity, because we have to keep the cost low. On the other side, we have seen that the bottleneck is in the interconnect, and the 10G Ethernet is really behaving good, but it doesn't allow us to evacuate nodes, I mean, to migrate VMs very fast. I mean, let me explain. When we're evacuating nodes, for example, we want to change a fan or change a power supply to a server, and we have to shut it down. And then we have to take all the 70 or 80 VMs that are running there to another server, which may be not in the same rack. It's in a different rack, or perhaps in a different data center. And we don't want the users to take notice of this evacuation, of this migration. So the latency is very important. So, I mean, an interconnect more than 10G would be ideal, but it's a matter of cost. I mean, eventually all the service providers that they are offering cloud services will try to seek for commodity solutions which offer bandwidth and latencies better than today. So we are not satisfied with what we have. Okay, thank you very much.
I would like to just to say that there are 3 authors that they have not hung up their posters. So please, anyone that has not hung up his poster to go and hang it. Okay? Thank you very much. So coffee, and please take a your cup of coffee and go to the posters and see all the work from the students that they have contributed their work to this summer school. Thank you.